you are still able to see my screen. Can somebody confirm?
Yes, sir, we can see it.
All right, great. So, good morning, guys. Welcome to the session. We are discussing chapter 17 of your prescribed textbook, Somerville. The topic is distributed software engineering, a very interesting topic. And it will become rather more interesting if you start correlating this with the technologies that you use today. Sometimes we use some technologies, but we probably don't understand the architecture behind it. Where does it come from? How it traveled, how it eventually metamorphized into something that we use today as various nomenclature exists, like cloud computing, Web 2.0. You have seen different applications on your mobile, on your smartphones. All that somewhere has a background into this chapter, distributed software engineering. So it's a very interesting chapter, as I said, and uh, we'll come across different concepts that basically we use today in software development, and that has transformed the technology of implementation of applications, uh, quite significantly. We will, in this topic, discuss distributed systems. We will discuss about client-server computing. We will discuss architectural patterns of distributed systems, and we will also, talk about software as a service, which is abbreviated as SaaS. In fact, if you look at the abbreviation, it would be more like it would be written more like that. Now, the people who understand Hindi, this word obviously is quite, uh, it's actually, or you have watched some soapies on your some of the Bollywood channels. I mean, rather, I would say your, your Hindi channels, or whatever you want to call them, which provides you different contents in Hindi. Then SaaS means mother-in-law. This is just to remember. I don't want to create any controversies, right? So SaaS means mother-in-law in Hindi. A good way to remember things. So let's go to starting this. Now, when we talk about distributed systems, well, to define it, we can say that it's virtually a large computer-based system, which is basically constituted by many different servers. These servers might be located at different locations. They might be located at, even in different countries or different continents, and they all work together to provide a particular functionality, a particular information system, a particular, a service or an application access to its users. So it's a collection of independent computers that appears to the user as a single coherent system. So the user doesn't, feel any difference whether the user is using a single system like a standalone system, or the user is using a collection of systems which actually share the processing load, and they are situated at different locations remotely, or they can be located at even one location, but in one premises, but they are different systems. So you have seen, some of you might have gone to a data center, and you might have seen those rack servers, as normally they are referred to. Sometimes they are also referred to as blade servers. So what you see is a big rack with all lights flashing around, a lot of network cables running from, in and out. And then you see some, mostly vertically mount machines. Now, these vertical mount machines are basically CPUs in their own right. They are full-fledged CPUs with microprocessors, with RAM, with main board. It's just that their form factor is sort of designed differently, so it looks more of like a sleek, insertable machine. The thing is, these rack servers work in a live mode. So basically, you can pull out a particular blade. That means you are pulling out a machine. And then you can also hot plug any machine into the servers. So if one of the machines uh, probably is not working properly, is misbehaving, and you need to reconfigure it, or you need to replace hard disk or something, one of the hardwares in them, you can simply pull them out, and then you can reinsert a new blade there, which doesn't impact the functionality of overall system. So that's basically, trying to give you a visualized picture of the system, uh, where you could imagine that, there is a substantial amount of, power and processing available in these machines. They work collectively, they share the processing load. So there is a very good redundancy, as we call it in our IT language, information systems language. Redundancy here is not a bad thing, it's actually a good thing, because redundancy, as you have learned in databases, is a bad thing. That means repetition of data means wasting your storage, your resources, and would be considered as a bad, database design. Here, the redundancy is very critical for smooth functioning of your systems. So if something goes wrong, it shouldn't disrupt the overall operations of your applications or the service that you are providing to your customers. So redundancy is considered to be a backup, you know, and it provides you, uh, uninterrupted service. That's, in terms of software availability. That's basically what it is, and that's what distributed systems are capable of providing. Information processing is distributed all over several computers rather than confined to a single machine. So obviously, that's a key factor of distributed systems. Distributed software engineering is therefore very important, yes, for enterprise computing systems. So it's very important to understand, how this architecture is formed and how it is implemented. Resource sharing, yeah, what are the key characteristics of your distributed system? And why do you have distributed system? Obviously, it's the resource sharing. That means you can share the resources. Distributed system provides you the flexibility of having the resources, at your disposal. And obviously, it provides optimum resource sharing. That means if, a section of users may not be using some resource, and another section of users may be needing more of that resource, or there's a heavy load on certain resources, then automatically these systems, distributed systems, are sophisticated enough to redistribute the processing load. So they can, uh, you know uh, very well utilize the whole architecture, in a more smarter manner. So it's not like one of the machine is lying idle, and another machine is, like, burning and getting hot, getting overworked. Uh, you know, so there's a load balancing factor where you can, redistribute the load, and then how you can basically make sure that your whole infrastructure is basically fully utilized. If certain of the servers, in fact, uh, or some section of the servers is not being utilized fully, it can even be switched off to conserve power. So, and most of this happens quite automatically through basically services like uh, virtualization technology, where you have virtual machines running these days. So this technology has gone into a new realm, because using it's not just distributed systems anymore. Well, that's what basic architecture is, but on the the higher end, it is basically distributed systems along with virtualization technology that does the magic for you, that controls the whole this very sophisticated architecture that you have today. And you call it with different names. You call it with cloud computing. Obviously, I mentioned about software as a service, SaaS. You call it as infrastructure as a service. You know, all that is all different names to it. But essentially, yeah, it is. So there are many different kind of implementations that you're going to see that happens, and it happens through distributed systems itself. So resource sharing is a key factor, as I mentioned. Openness, that means the technology today allows you to utilize different vendors, hardware and software as well. So distributed systems support openness. That means you can use different vendors. Earlier, it wasn't the case like that. Earlier, you had to be logged up with one particular vendor, because there was no interoperability between different systems. But today, due to some protocols, networking protocols available, uh, it is possible that different systems communicate with each other. Before, most of the systems used to work with the proprietary protocols like IBM, and all of them had their own communication protocols. But today, most of the systems use or are compatible with TCP/IP protocol. And because of that, these systems can now interoperate. So it's openness in the architecture. Concurrency, which means you have multiple systems uh, that are running in parallel. And that means they provide a very powerful processing hub, a very powerful high performance architecture. You might have heard about a name called high performance computing architecture, H HPCA, but basically is the name there. These servers sit in Cape Town, and especially the science people, the people who are doing research, especially like genome research, uh, DNA sequencing, or some other high-end research, probably in the field of physics, uh, like uh, you know uh, analyzing some data coming from probably some space or something. I will mention about an interesting example of that probably in the end of this session. So all that is there. So HPCS stands for High Performance Computing Architecture. Again, it's an example of your distributed systems, because the server sits at a remote location, and these servers, obviously, which are multiple in numbers, they can provide you a very powerful computing, something that you would need a supercomputer for. So they sort of provide you sort of a supercomputer kind of functionality, although it's just a collection of many powerful computers running concurrently in a synchronous manner that makes this possible. So these are some of the things that are very interesting to know what exactly lies out there. And as I said, mainly sciences and then some other physics research, or maybe some other high-end computing would be high performance computing would be utilizing these architectures more often than not. But even today, a common person utilizes these architectures. So when you are using any cloud application, when you're using your Google Docs, when you are using You're creating a Google Doc, you're creating a Google Sheet, uh, you are using your Google Drive, you are actually utilizing this distributed systems in the background. Scalability is a very powerful factor of distributed systems, which means that you can scale them. Now, what does scalability means? Scalability means that, say for example, you are having, uh, you know, 1,000 users using your application at one time, probably, or you can choose or pick any number you feel like. And now, all of a sudden, the user using your application, your service actually changes to probably 100,000. So will your application cope with the increase of that number? That is scalability. So scalability means that your application should be able to take additional load, uh, you know, and should be scalable enough to increase its capacity to handle uh, more number of users when they try to start using your system. So it can automatically, and there are some terminologies there in scalability as well, like scale up and scale out kind of. I'll explain that. So scalability essentially means that your application is capable enough to handle an increased load on it, an increased processing load, and it can also increase the throughput, by adding new resources. Fault tolerance, when, as I say, these distributed systems are redundant systems. So they have redundancy in them, which means that there are backups available to you. And they are, since many systems running in parallel. So if one of the systems goes down out of many, automatically the other systems would take over that load, that processing load. So automatically that processing load is handled by the existing functional machines. So that is fault tolerance that you get. So your operations continue even after the fault has occurred. It's not like you have lost your work. Probably when you were saving your document in Google Doc, probably one of those blade servers just crashed, or just stopped working, but that doesn't affect your operations. You wouldn't even know or feel or realize that such a thing has happened because of the same sophistication that has come to these distributed systems now. And all fancy names are given to that: cloud computing, as you are very aware of. But essentially, it is the distributed systems architecture in the backdrop of all these systems that you use, all these services that you utilize. Uh, so there are some disadvantages, if you can call, for distributed systems as well. And this could more be attuned to the legacy distributed systems mainly. But as I said, distributed systems have also evolved much with time. So you can say distributed systems are more complex. Yes, they are definitely very complex technologies. Uh, and designing these kind of systems is not as simple as designing a single processor system or single process application. So today, but this technology, as I said, has already become a full ecosystem. So many users or many developers actually develop applications that run on distributed platforms, but they don't even realize. Some of them are making applications, but they don't know exactly, how these APIs are in the backdrop working on a distributed system, how they can plug in into, existing APIs, how they can send their, SOAP data. SOAP is a protocol, by the way, here. SOAP, System Object Application Protocol. It is a way where some application exchange messages or they communicate with each other using XML uh, format, XML, tags, XML language. So all that happens, sometimes obviously, as I'm mentioning, the developers may not also be aware of this architecture in totality, but they are making applications. Well, obviously they have been trained to do that. Probably they may not understand the whole architecture behind it, but they're simply making these applications. So they are definitely very complex applications. Uh, you know, but obviously there are technologies which, or there's like a full ecosystem now. There are these kind of full, uh, you know, architectural frameworks that have been created to make things a bit more doable and manage this complexity. So complexity obviously arises because different parts of the system are independently managed, uh, you know, over the network. So there are, multiple different sections which are running in different parts of the network, or on different locations on the network. So today, a lot of that is automated. Technology obviously has overtaken and made these things a bit more manageable. So it's not like it is just the complexity. The complexity is there, of course, in the background, but a lot of that is abstracted from the developers themselves. So there is no single authority in charge for the system, so the top-down control is impossible. Distributed systems is still controllable. So this statement is, uh, not exactly correct, but anyway, uh, it could be said that if there are multiple stakeholders involved, and sometimes there are multiple stakeholders involved, and they all participate, so that could make the control of the systems a bit difficult. Uh, but if the system is owned by a particular company, obviously they probably would have a whole arrangement, a whole kind of policy and strategy to control these systems. But that could be seen as a drawback in some of the systems, as I mentioned. When we look at the distributed systems. Some other issues, will we say these are like some of the issues to be considered when we're talking about these distributed systems. Transparency is one of them. And transparency means that to what extent should a distributed system appear to the user as a single system? As we mentioned right in the beginning of this lecture, that these distributed systems basically appear to the user as a single user system. I mean, the user cannot distinguish whether they're using one single server or there are multiple servers running behind the scene. They don't have any idea because it's all abstracted from them. So the point is, transparency obviously is a good thing. So whether the user should be made aware that they are using multiple systems, or they don't need to know that they are using multiple systems. I believe transparency is a good thing, but also you can make the user understand that this is, in fact, if you try and communicate it properly, excuse me, probably they will appreciate that there are multiple systems running behind, and you tell them that this is redundancy, and you explain the meaning of redundancy to them, that this is like backup. So if you have 5 horses, now one of your horses is sick, or maybe 2 of your horses are sick, you still have 3 horses to use, which is a good thing, rather than having only one horse and that horse is now sick today and you cannot ride that horse. So you can explain that to the user. So the user need to be and, clear. I would believe that the user should be made aware and it can be communicated in a positive manner. So the user feels more confident about using these systems. Openness, am I getting any chat messages. I just want to check that. I believe if I get a chat message, it would show up on the screen. I'm not sure about that. So just checking if there is anything. Okay, I'm just getting. All right. So I don't see anything yet, but of course you can put your queries in the chat. I believe I will be able to see the notification on my screen, uh, and you can unmute yourself and speak to me as well to get my attention if you see that that's not happening. Openness. Should a system be designed using standard protocols that support interoperability? Now, I think that will be a very good strategy. Openness, that means using those open source technology is a good thing. And since it has become a need of the day, even some of the very closed source companies actually have joined the open source movement. A good example of that is Microsoft. Microsoft earlier was very against open source movement, and you very well know why, because they wanted to sell their licenses and their licensed software to everybody on the earth. But when they saw that the open source movement has picked up, and this is changing the whole approach towards collaboration, system development, uh, you know, and participation, then they had no choice but to join it. And today they are doing very well. In fact, they are promoting open source movement uh, to some extent. Obviously, that doesn't mean that their Windows have become open source. Still, some of their key softwares, whether it is their operating system and their Office, uh, but a lot of their Office has become open source, by the way, because if you look at the applications like Office 360 and all that, they use a lot of open source technology today, and that is how they are able to integrate on internet, on the web, with many different applications as well. So it's their openness means the system is designed using standard protocols that support interoperability. That is definitely the need of the day today, because there is a lot of collaboration that happens between different providers, service providers, vendors, software developing firms, and so forth. Scalability, yes, that's a very important aspect of distributed systems. They provide you scalability means that they can be you know compatible to uh, more number of users, and they can automatically adjust and reconfigure their workload uh, by allowing more users to use their services. So scalability and how much scalable your application should be, these can be some of the design issues that we can discuss. Scalability, of course, comes with distributed systems, but how scalable it can be, whether it can handle, 50% more load than it is designed for, or it can handle 100% extra load. That can all be discussed when you are designing these systems. Security is a big concern when it comes to distributed systems, because the whole idea is that the servers are actually lying at a remote location. They are lying in different other person's control. So many people, I would believe, initially never felt very confident about distributed systems or cloud computing. And as I say, the cloud computing architecture uses distributed systems in the backdrop. So many people had, and many organizations even had their own apprehensions. But I believe this has not stopped the organizations or even the individuals, users, to use cloud computing systems. I mean, I rather have found them more reliable personally than running my laptop, which can crash even today. I always run on This is a bit of an old machine. It always run low on hard disk space. I have to close some applications to run another one. So it's always a little bit of a challenge. So that's why I trust the cloud architecture, the cloud platforms more reliably in terms of reliability, I mean, than my standalone system. But many people still feel very uncomfortable, or they want things rather in their own control, so to speak, and they may have apprehensions about using some of the systems uh, like distributed systems and, as I mentioned, cloud computing applications. So security is definitely a very important aspect and a very important factor. And organizations developing these systems, providing services uh, through these architectures should be very much aware of the security aspect of it. So that's the point. The quality of service, yes. What is the quality of service? Quality of service, obviously, one of the main aspects of quality of service is uninterrupted availability of a resource. So how's the quality of service? I mean, if you have used Google Docs, and obviously you want to compare that with your MS Office, or let's say you comparing it with MS Word. So how do you find, in terms of user interface? How do you find in terms of smoothness and efficiency of that application to function? Does it look smooth while you are working with that, or does it look glitchy? Like it hangs frequently. These are all factors that can be considered when we're talking about the quality of service. So it's very important that applications are designed in such a way that they provide quality of service to the user. Failure management, of course, how the system failures be detected, contained, and repaired. That's basically important, right? So as I already mentioned to you, today distributed applications have a very good redundancy uh, inbuilt in them, so which takes care of issues of like uh, failure management, which means that the the possibility of your systems to fail is very minimal, because there are always backup systems that can handle and that can redistribute if one of the systems or one of the machines, one of the servers actually go down. Other systems, other servers would be automatically overtaking that processing load for that system. So that's basically also a very critical factor to determine when you're developing your distributed systems, that the failure management uh, has to be considered, which means the failure has to be made almost negligible. So that is the goal of designing these distributed systems. Uh, Transparency, ideally, I've already mentioned that the user should the user be aware that the system is distributed, and the service. I believe in transparency, so I would believe yes. The answer of that should be, according to me, that the user should be made available, should be made aware, rather, of the fact that they are using distributed systems. That means there are multiple servers and that kind of architecture behind the scene. So what they say is ideally the user should not be aware that a system is distributed. Now this is being mentioned here that the operations or the service should be so smooth. I believe that the user should be educated. And if you are educating them properly, it would rather be considered more of a positive aspect than anything negative, or they're scared of it or anything like that. If you communicate or educate them properly, with the technology. But sometimes it does happen that some people believe no, too much information can be confusing for the user, and they should not be aware that the system is distributed, and the services should be independent of the distribution characteristics. Now, here what they mean essentially is that the user shouldn't get a feel that this application is running from multiple servers. What they really mean is that it should be smooth enough. It should be absolutely smooth, and it should be performing to that optimum level that they realize, they feel that is just one system that they're using. It's just that they're using one service, one system. Uh, Although behind the scene there are multiple systems running their applications. So that's basically the idea, that it should be abstracted from the user. The complications of the technology or the complexity of the systems that exist behind the scenes. So somebody would say, no, 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 don't bother the user with the complexity of the system and the fact that it is a distributed system. They should just simply see that this is one service they are using. This is one application they are using. Whether that application runs on a distributed system, how does it work? And all the technical complexities behind that could be all hidden or abstracted. Now, that could be one, a philosophy. That could be one strategy of the company if they want that. But in practice, this is impossible. That's the point here they are making, that because the part of the systems are independently managed and because of network delays. So that's another thing to be looked at, the network delays. But that doesn't mean that a system still can be high performing system, and it can work as a standalone system or as efficiently as a standalone system, even though it is being implemented as a distributed system. So often better to make, now here they are obviously coming to their senses. I think that is a statement to be given a thumbs up, that it is better to make users aware of the distribution so that they can cope with the problems. I mean, they should know what exactly or what kind of systems they are using. As I said, you can mitigate their threat, their apprehensions, or their whatever fears they have in their mind, by properly educating them and telling them how the technology works, which is a better strategy rather than keeping them in the dark. So these are a few of the things I think which has to be made clear. Now, most of these cloud computing, as I mentioned, distributed systems run on cloud computing. Today, rather, it's the other way, that your cloud computing applications utilize the distributed system architecture behind the scenes. So to use these services, use these applications, you need internet, right? So you need to make aware that the user is aware that this is a service being given to them over the internet. Now, if the internet connection is unstable or the internet is not properly working, uh, they have to be careful. It's just like you're using some Google Doc and you are just, just keep on, you keep on like typing, creating your documents, working on that document for a long period of time. But your internet connection is unstable and some of the changes may be lost because of the internet connectivity. Although I have rather seen these applications have become so reliable and so efficient that either they will notify you that the internet connectivity is not working or whatever, but you still have to be careful about that factor. That just ensure that the internet connectivity is working, and if the internet is not working, then obviously you know your data will not be, your work will not be synchronized with the servers. So that's one you know a factor, and that is why the transparency becomes, as I mentioned, more important, that the user is made aware that you cannot be simply working uh, you know uh, uh, like assuming that you're working on your standalone system. This application service is being provided by remote servers to you. And to have that service working, there has to be a stable internet connection. So if the internet connection is unstable or not working properly or not working at all, that obviously will impact the synchronization. So your work might be lost. You might be thinking that, yes, I'm doing and I'm working and it's being saved. Well, today you've seen that your Google Doc saves it in real time. So even if you type one character, it is still saved. Automatically, it's gone so efficient. But in some cases, it might be that you didn't realize the notification, or, you don't check the internet status, and then you are assuming that it's all, you know, connected properly, and then you lose some work because of that. So that these are some of the things to be, uh, contemplated when you are working with distributed systems. So to achieve transparency, resource should be abstracted and the addressed logically rather than physically. So that's what basically happens. Uh, this is uh, this is what happens. Abstraction is a key factor of these systems today. You don't really realize when you're using any of these applications that you're using a distributed architecture behind the scene, and these kind of problems are addressed logically. These are obviously logical systems, not physical systems anymore, through virtualization technology, and uh, and that's how all this happens. Middleware maps logical to physical resources. So basically, as I say, what is a logical resource? A logical resource is like you see your Google Drive. Now, Google Drive, in which you have stored your data, your files, and all that, probably have got that data distributed on multiple servers. And I gave you the reason why, because of the redundancy and the architecture that is needed and that is provided. So it provides you a backup. You won't lose your Google Doc file, even if few of their servers go down, as I mentioned earlier, because of this architecture and this technology working behind the scenes. So your Map Drive, your Google Map Drive, or your OneDrive that you use in Microsoft, they are logical drives. It's not a physical drive that, which is uh, given to a particular user at one single time. It's basically multiple users are using their resources, and to them it appears like one drive where they can save their work. You can actually install an application of your Google Drive on your system, which will show you like you're using your local drive, like a C drive, just like you use on your computer. But the fact is that it's logical drive, it's not a physical drive, and there is a system. There is a technology called middleware technology, which maps logical to physical resources. So this is again, as I said, the complex technology that works behind the scenes to provide you the functionality and to provide you the mapping of your logical to physical resources, which means, as I mentioned, your Google Drive is a logical drive, but somewhere the data is stored physically on some hard disk, but it's not present on one single hard disk. Probably it may be spread out across different servers that have different hard disks, multiple hard disks many times. You heard about RAID, that which is the again redundancy within a server. That means the server has multiple hard disks. So if one of the hard disk fails, other hard disk can actually regenerate that data. So we have different RAID configurations. So here we have RAID 3, RAID 5, and so forth. You can research more about this. It's basically called redundant array of uh, independent drives. Somewhere you will see written inexpensive drives, but that's okay. It's basically a redundant array of independent drives, which means multiple drives are put up into an array. 3 drives, 5 drives, different other array configurations exist. And it is to provide that, backup, that automated, uh, a fault tolerance to your system, to your servers. So this is one, and then as I say, there are multiple servers. Yeah, as I mentioned about the rack servers and those blade servers. So you see multiple servers. The server itself is a collection of multiple machines, which work all in a synchronized manner. So they use some sort of middleware technology to redistribute whatever, like if you're saving some data, that data is redistributed and that might be stored in different hard disks. Why? Because to provide you fault tolerance and redundancy, as I mentioned earlier. Okay, openness. Openness means open distributed or open architecture. So today, many of, or rather most of the leading companies support the open architecture because that allows them to create systems that can interoperate. Today, with internet in place, with the technology and with your whole Web 2.0 or whatever you would call it, it's impossible for any company to work in isolation. There were days when IBM networks were only IBM networks. I mean, the servers were from IBM, the the routers were from IBM, the network interfaces were from IBM, and many of these companies like AT&T and IBM and other big companies had their own private networks, and they were operating all in silos. But then comes internet, and these silos break, and all the systems join each other. They start getting interconnected with each other, and that is how your internet is born. So your internet is a network of networks. These networks used to existed even earlier, but they were just not interoperating with each other, but now they are actually. So that's basically what it is. So open distributed systems are the systems that are built according to generally accepted standards. There are standard protocols that are being used, uh, and standard technologies that are being used by most of these companies, uh, where they operate or they interoperate with each other easily and freely. Uh, the components from any supplier can be integrated into the system and it can interoperate. Now, this is basically you can call it as you can call this as today's requirement that none of the companies can operate in silos. They have to develop systems that can interoperate with each other. So this is the trend, and this has become a standard now in the industry. Openness implies the system components can be independently developed by any programming language, and if it all conforms to the standards, obviously it does. They use standard protocols, so they will work with other components. So that means they will all work with each other. So that is why there are some standard protocols and some standard APIs. API is application program interface. So these are some of the technologies that facilitate interoperability between different applications, different services that are provided, and it provides that openness that we are discussing here. Web services standards. Uh, Obviously, most of the applications are provided to you as a web service today. That means you can access them over the internet using your browser, just like Google Doc. You don't need to install uh, any application except the browser, which even comes preloaded on many operating system platforms. And then you can download others for free, like Chrome. Uh, so if you're buying Windows, obviously you're buying a Windows laptop, you will have Edge sitting on it already. But then you can also download your Chrome, and you can download your Firefox. So, and you can use any web-based applications, cloud-based applications there easily. So this is, web service standards for service-oriented architectures, and they were developed as open standards. So it's an open world when it comes to the systems today. It's very much, riding on the architecture which is open source, systems, open source architecture. And the protocols are standard protocols. They have become the standard for all different applications that use them. Scalability is a very powerful feature of distributed systems. That means, uh, you know, the systems has the ability to deliver a high quality service that demands on the system increase. So if the user base increases, that means the number of users double up, triple up. The applications that are developed today using distributed systems are capable of, or should be rather capable of, uh, providing services to the increased number of users. So that is basically scalability. And this is one of the reasons why we have these technologies being utilized today. So when we talk about scalability, we talk about the size. So it should be possible, to add more resources. That means to increase the size of your system resources uh, to cope with increasing number of users. So that's basically what it is. Distribution is obviously, when we're talking about distributed systems, distribution is definitely one of the parameters there. It's a distributed system. So that means the resources are distributed. So it should be possible to geographically disperse the components of a system without degrading its performance. So they are saying that the resources should be geographically dispersed. Now I would like to ask you, what could be the benefit of dispersing resources geographically? And that also becomes a key advantage of distributed systems. Anybody, you can unmute yourself and give me an answer. Or you can also put that into chat. What do you think is the advantage, or if you see that as a disadvantage of the distributed nature of the systems? So distribution, which is obviously the property of a distributed system. How do you see it? Do you see it as an advantage, or you see it as a disadvantage? Hello. Is everybody gone fishing? Hello. Hello. Anybody there? Guys, I just want to be sure that I'm not talking to myself. I'm talking to some real people out there. Okay, just say yes, we are there.
Yes, we hear, sir.
Okay, good to hear that. I was feeling scared actually.
Oh, we hear, sir. We listening.
All right. Okay, so probably I'll answer it, in coming lecture a little bit more in detail. But essentially, to say that distribution helps a lot in the terms that it provides localization of data. So that means if you have distributed systems, then probably, say for example, Google is providing you their cloud services, and you're using their services like Google Docs and Google Drive. So if they have put up a server, say for example, in South Africa, or at least in Africa, in the continent itself, and they are storing the data in a more localized manner in South Africa. So obviously the data that you are accessing uh, is actually being stored in South Africa. So it's not leaving the country or the continent. So that is basically localization of data. That improves the performance quite significantly. So if your data is being stored or saved in US, now you can imagine that it has to travel through an undersea cable, one of those undersea cables that gives you internet connectivity. And these undersea cable will carry your data to US. Now it has to travel, thousands of miles under the sea. Uh, it will feel a bit cold, huh? This is just kidding with you. So these technology and systems are quite efficient these days. So you don't see, even if it is traveling to US, the latency is not uh, that much, because they are very high speed communication channels, communication media. It use all the fiber optic and all that technology that you have read about. So it's very efficient, but still, you would agree that if the data is localized, so that means if your data is stored in South Africa, South Africans obviously will find that more efficient, and there will be less latency in terms of accessing the data or accessing that service, compared to if that service is being stored in US. So that's a big advantage of a distributed system. As I mentioned, that you can do data localization, right? So the other thing is manageability. It should be possible to manage the system. Obviously, when any system becomes complex and it increases in size, the management of that system becomes difficult. So, and at times, you wouldn't even imagine, but some of the services being outsourced these days. So you might be using an application or a service on internet. Probably today, every single platform, every single software is available as a cloud service, whether it is Adobe, whether it is Photoshop, whether it is Microsoft Office. You have heard about Office 365, haven't you? So Office 365 can be used completely without installing any uh, Office application on your system through your browser. So you can use your Office 365 over the browser. You don't need to install any software on your system except the browser, which, as I said, already is pre-installed when you buy your Windows operating system. So, uh, you know, and then these services, uh, some of the services would be outsourced probably to some other company. So it works like this, just like your car manufacturing industry. Now, BMW is making your favorite car, um, but BMW is not making every part of that car. The tires are being produced by somebody else. The battery comes from Excite or some other big brand company, where whatever they use. The tires are from Dunlop, say for example. Uh, your Probably the audio systems come from another vendor. So there may be, different systems outsourced to different other companies. I can tell you for sure, every chip that goes into your car mostly is manufactured by what is that Taiwan company, the famous Taiwan company, Taiwan Semiconductor, something like, yeah, it is called something like TS something. It's one of the biggest chip manufacturer companies in the world. So 80% of the chips are manufactured in Taiwan, or many of them are in, the companies, Taiwanese companies, but maybe manufacturing in China, or probably in some other country as well these days. So basically, some of them has come to India as well. They have set up some factories, some plants in India. So you can imagine that all different vendors may come together to provide one working system. So this is basically, sometimes it becomes difficult to manage that. So manageability is the big, one of the big factors when you are making these kind of systems. So it should be possible to manage a system as it increases in size, and even if the part of the systems are located in independent organizations. Now that's what I'm trying to make. The point that I'm trying to make it is this, that today there are different vendors which come together and provide services that you use. It's not just one organization anymore. There are a lot of organizations participating probably, and they are some of the services being outsourced to some other companies. So even if probably one of the companies want to have their applications, or their servers set up or their data to be localized in South Africa, they'll use one big data center that may already be existing or somewhere sitting already working, and they'll hire some servers there, and that's where they'll deploy their applications. So it's all it works in that way, and there has to be a proper management system, the management policy that should be put behind these systems. So it is a distinction between scaling up and scaling out. So scaling up means you are now putting more powerful systems so they can take more load, processing load for you. Right? So you are basically increasing the capacity of your systems, your servers. That's what it means essentially. Scaling out means that you're not increasing the power of your servers, but you are increasing the system instances. So that means your servers are still the same servers that you had. I mean, their power is still the same, but their numbers is increased now. Or what you have increased, you have increased their virtual machine or virtual images, So today with virtualization technology, what you're using something called virtual images, right? So there is a virtual image that is being used, right? So we call them as virtual machines, although as I say, it's all virtualization technology. So your virtual machines or the number of your virtual machines will increase. So it's not like the capacity of your server or the processing power of your server will increase, but collectively the user will see enhanced performance, of course, when the number of virtual machines increase. So this is basically what the technology is all doing these days, the tricks that it is doing these days. So you'll see that scalability means that you're going to increase either you're going to increase your server power, you're going to have more powerful systems, or you may be scaling out, as it's being mentioned here, means that your server power is not increasing, but the number is increasing, or the virtualization makes that more virtual machines are participating in the process. Security, when a system is distributed, right, obviously it can be critical, that a system can be attacked from outside, because as the number of instances increases for any security of the system, you would see that it also makes it more vulnerable. Hello, was that just a bit of an interruption? I guess. I hope it wasn't any. Yeah. Okay. I thought somebody is trying to communicate. So what I'm saying here is that if the number of instances increases of the installation, that means the system is distributed, which also makes it a bit more vulnerable. That, if a system is installed in 10 different locations, say for example, maybe out of that one, a location is very vulnerable, is not protected properly. So that provides you a weak point, for the system to be hacked, to be attacked, right? So with distributed systems, there's a bit of a challenge of security. Compare that with one centralized system. Now, in one centralized system, you only have to safeguard or secure one premises, one server, and you are done, right? But in distributed systems, because it is spread out in many different locations, you have to be careful enough to make sure all the locations are safe and they are, secured in a well-deserved manner. Otherwise, one of the location which is not properly protected can become attacking point, and using that location, the attacker can also attack other sites, because the attacker is now in the system. Attacker has intruded your system, and from there it can launch more attacks. It can do more damage. it can create more problems for the system, as such. So if a part of the system is successfully attacked, as you can say, that provides a backdoor. So that becomes a backdoor into the other parts of the system. So these are some of the challenges of your distributed systems. So all the locations of the distributed systems should be well protected. So these are some of the challenges and these are the difficulties in distributed systems because different organizations may own different parts of the system. So as I mentioned to you earlier also, just like it happens in your car industry, that different components may be manufactured by different vendors. Similarly, today also different functionality, different components that are working to form that distributed system can be owned by different providers, by different companies sitting in different locations and providing those services from those locations. So maybe somebody is providing storage, somebody is providing hardware, somebody else is providing something different. There may be some specialized functionality which may be provided by a particular organization, and that is being used as an API, which obviously means that it is being remotely accessed as a service and provided to its users. So these organizations may have mutually uh, incomplete security policies and security mechanisms. So that may be a challenge, although obviously company tries their best to cover these risks, but still that could be a challenge, for many organizations. So you've already read about some attacks. Some of you are aware of these attacks. And I also covered up some of that in security engineering when we discussed about some attacks. What kind of attacks can happen on distributed system? Obviously, one of them is interception, where the communication between parts of the system is intercepted by an attacker. So interception is like somebody has, and the example is man in the middle attack, So you are aware of that man in the middle attack, right? Monkey in the middle attack. These are some of the examples of interception. Interruption obviously is where the system is attacked and it cannot remain functional or it cannot be delivered as expected, which means it is not providing, it's not running properly or it's not providing the services to the users. Denial of service attacks, DOS attacks, is a very common example of interruption. So which means that a particular, in distributed systems, we call a particular location where a software instance is running as a node. You may have heard this word, and then I'll come back to you with more examples of that. So a particular node is bombarded, and with illegitimate service requests. That's exactly what the DOS attack means. So it basically bombards a node or a server as you would like to understand it. With illegitimate service requests, it floods that particular server or node with fakely created service requests, and it becomes so overwhelming for that server or that node that it cannot handle them and it just crashes down. So that's what it is. Modification, where the data and services of the system can be changed by an attacker. Data can be modified, or some of the rules of that software can be changed. Some information can be changed, and that can be causing damage, causing data integrity problems, and all that. Fabrication obviously means putting fake data into the system, inserting fake information into the system, where the attacker generates information and puts it, and that should not exist. So basically, you've read that in your security engineering also, in that health care system, that the attacker actually plants some information to defame like a celebrity, say for example. So the celebrity is, probably not suffering from a particular disease, but the attacker fabricates some, you know, test results, test reports, and puts that on the system. So now, nobody wants to like hire that sports person. Say, for example, that celebrity is a sports person because of that fabrication information, and that creates damage to the career of that person. So these are some of the examples here, and you are aware of that. We have discussed that in previous chapter as well. So fabrication can be one of the attacks. So two type of interaction between the component of the distributed system is obviously a procedural interaction and message-based interaction. Now, procedural interaction is obviously through functions. There's a technology which is still being used, although people don't know about it. It is called RPC, Remote Procedure Call. Now, remote procedure call technology which has been used in many of the systems, rather you can call them legacy systems now, RPC. Now in RPC, which means that you can call a particular procedure. Procedure means function. You can call a function or a method remotely. So basically one software component is sitting here. Let's call it C1. And this is giving a call to another component which has another method sitting on it or a function sitting on it. And this function is called, like calculate tax, say for example, right? Cal tax, let's call it very simply. And it would call this function to do the tax calculation for it, and then eventually return the results back to the previous component, the calling component, right? So the tax output will go, final tax output will go to this component C1. Now that happens through remote procedure call. It used to be like that earlier. There are still some systems that use this technology, but this technology has now been superseded by some other technologies. One of them is message-based interaction. Now in this, basically the two systems are engaged. Both the components are engaged, with each other in a like a a proper two-way communication. Like they are basically you can, to understand this, you can say that okay, this component calls this other component and asks for some information, and this component processes that information and gives it back to this component, but they are together in a session, when they are communicating. Now that is more resource consuming, resource intensive. The other form of that could be, now this is like somebody is calling you, your friend is calling you and asking some information from you, and you are struggling to even remember that, and then you say, oh, I don't remember. You're feeling pressurized as well to provide that information. But on the other end, you say, okay, just send me a WhatsApp message, right? And the WhatsApp message comes to you, and then you have got it, and then you have time to think, and then you can obviously reply to that, after putting your thought process to it. So you're not actively engaged, all the time, in that communication. So you can, I'm just giving that example to understand the technology, which is your message-based interaction. So you got a WhatsApp message, you read it maybe after after 5-10 minutes, and then you had your own time to think about it, and then you can respond back. So you are not engaged, for a longer period of time with that particular person. So computer systems also work through messages, and I did mention to you about SOAP message, which is known as a simple object access protocol. It is an XML-based technology that communicates using XML format. So it sends messages in XML format, and the systems can work fairly independently. Uh, they don't kill each other's time. They don't consume more time to be engaged with each other. And this allows one system to serve, or one component to of a distributed system to serve many components at the same, in a specified time. So all it has to do is send the same message to multiple, components. So just like you do your copy paste of your WhatsApp messages, when you want to send same greetings to everyone, you create a greeting and then you would copy paste that to all different friends. Something similar can happen there. So you don't have to personally wish, and you can also do send to all kind of thing. So that's how the message-based systems interact with each other. They send XML messages, and the input and output obviously travels through these, SOAP messages, as I mentioned to you, which is designed in uh, XML format. Normally it's called SOAP envelopes. So in SOAP envelopes, your message can travel discretely to different other components, and a lot of that happens quite automatedly. So there is no user intervention in between. So it's basically if you're transferring, like today banking systems are very integrated with each other. So if you are transacting and you're sending money from like a bank called Standard Bank to a bank called FNB, right? Now that obviously will go as a from the Standard Bank servers, it will travel to uh, FNB servers using a SOAP message. So, and at the same time, Standard Bank can send another message to, like NetBank, right? So there can be more uh, communication channels established at the same time during a short span of time with multiple stakeholders, and it becomes more efficient to communicate that way. Procedural interaction between a dynamic. Okay, now here basically there's an example given here. How a procedural interaction happens. That means two parties are engaged with each other, communicating with each other face to face or directly. So basically, you go to a restaurant and you order tomato soup, uh, and the waiter asks or the waitress asks you, and to follow, what else do you want to order, apart from the tomato soup? And you say, I want to order fillet steak or whatever. You can substitute that if you are vegetarian, samosas, right? How would you like it to be cooked? Or maybe you want to obviously order some curry. What would you like to be cooked? And you say rare, please. I understand uh, the meaning of this. Probably I'll Google it. What does that really mean? Rare in terms of fillet steaks, eating it probably in some way. Uh, whether it is raw, I don't think so. You can't eat raw. But yeah, if you know, you can tell me what exactly this is rare. You know, you can educate me there. But anyway, this is sort of a communication happening between a, a customer and a waiter. And if you convert that into XML, this is how this would look like. So there's a tag created called starter, and this can be like standardized. Okay, now some of the restaurants these days give you a tablet and say, okay, here you can place your order. So they have standardized that process. Obviously, they have built an application, and you select what you want in starter, what you want in main course, and obviously that information, if it has to travel to another application, to another server, can go as an XML file. And this is basically the structure of an XML file, right? These are XML tags here, starter and the end starter tag here, and then you have these attributes here. So one of the tag is dish name. Dish name is soup, and the type is tomato. Soup type is fish. These are the options that you're giving. Pigeon salad. In main course, you are giving dish name is steak, and the type is sirloin. I don't know how to even pronounce that. cooking medium, right? Okay, so rare probably could be like less cooked, I believe. So again, dish is steak and the type is fillet and the cooking is rare. That means probably it is quite raw, not too deeply cooked or deeply fried or something. All right. So this example of your XML file. So any information can be exchanged using XML, tags. And I did mention about the SOAP protocol. These are two things you can Google and try and learn more about it. Of course, you know XML, I'm sure. You can learn more about the SOAP envelopes and all that. So many applications would use this type of communication protocol to communicate data with each other, and that's what today happens. And many applications, are already automated to communicate to other. So basically, when you, as I gave example of a bank transaction, so whenever that bank transaction would happen, automatically your standard bank servers would communicate that information whenever they have done a transaction. Uh, so they would say, account information will go in probably in an account tag. So you will have an account tag here, and the account tag would be simply looking like this account. Uh, Account name tag will be there. Account holder's name will go in certain way. You would say account type will go there. Type is the check account or it is a savings account. All that will go there. So in that same format, your information can travel between two different servers or two different components of any two different servers. So RPC call, as I mentioned, in Java, this technology was called RMI. If you would like to know, it was called remote method invocation. Remote method invocation, RMI in Java. So it can be implemented by different technologies differently. Remote procedure call obviously means that one component obviously calls another component. And there is a middleware sitting which facilitates this communication. So the middleware in the system intercepts this call and passes it to the remote component. So this is how the distributed systems, if they are using RPC as a communication protocol, they would utilize. This carries out, this carries out, all the required computation. And this is facilitated by a middleware. And then it sends the results back to the calling component. So the results go back to the calling component. So that's how this communication happens. So the problem with RPC is that it is very resource intensive. That means the caller and the callee needs to be available at the time of the communication. If the caller is just like, as I said, if you're trying to call somebody, the phone they must not be on another call. But you can send a WhatsApp message to person even if the person is on another call. So you can understand, I'm giving this analogy of WhatsApp to make you understand that you can still communicate if a person is busy through a WhatsApp message. So when the person obviously is available or is free, will read your message. So that is less resource intensive, that is less time consuming for two persons interacting with each other than simply making calls to each other. So that's to understand this technology. So they need to be available at the time of communication, and they must know how to refer to each other. So that's basically what it is. The alternative to that RPC is message passing, where you do communicate through messages. So it's called message-based interaction, right? So normally involves one component creating a message and the details of the services required from the other component. So you just send a XML message, right? Or a SOAP message, as I mentioned to you earlier. So in XML, you're sending the SOAP message. So XML technology allows different components to communicate with each other using these SOAP protocols. So through the system middleware, this can be sent to receiving component. The receiver passes the message. Obviously, the message has to be understood and decoded in a sense. And then this is used and it carries out the computation. And then again, the results are sent back, are sending the component and then the message for the sending component with the required results. So the results are sent back to the calling component again for the messaging component, right? So what is the advantage of having a message based approach? Advantage it is not necessary for the sender and the receiver of the message to be aware of each other. They don't even need to know each other. They can simply communicate, through the messages without even knowing each other. And they communicate through the middleware. So it is more efficient. It is less time consuming. It is less resource consuming mode of communication between components. And they are more freely available to take multiple requests, through this system. And since, as I say, it's automated technology, automatically they can answer to the requests when they come in, any requests come in, and it keeps some data of that. So APIs are there, they have the listening components. They have the listeners. Whenever the request comes, they will capture that request, uh, give the response, and the job is done. So there is no need to have a continuous live communication channel engaged for this process. It's a very short-lived communication that happens, and it doesn't consume resources much. So that's the advantage of having a message-based systems. Uh, Middleware is basically the technology that facilitates communication between two components. So the components of the distributed system may be implemented in different programming languages and may execute completely different type of processors. So they run on different machines, right? They uses different technologies, and they might be using different type of data formats and all that. So their information presentation and protocols of communication may be all very different. So there you need a technology which sits in the middle, like a middleware technology that can manage these diverse parts and ensure that they all can communicate and exchange data. There is a term called Corba. You can Google that term, Corba. It's called uh, Common Object Request Broker Architecture. Now, this is a technology that is used between components that are, developed in different programming languages. As I said, RMI, I talked about RMI, remote method invocation. Now, RMI means that a particular Java program or a Java component can only communicate with another Java component. So this component C1 has to be in Java, written in Java, if it needs to communicate to this component C2, that also has to be written in Java, right? But if you're using a technology which is like open technology like Corba, uh, a Java component can also communicate with a component written in, probably Python, right? So the C3 component is written in Python, and you can communicate with each other. So these are some of the technologies that allow, and then these are middleware technologies that allow different components to communicate with each other. Okay, this is a diagram illustrating the job of the middleware in a distributed system. So basically, what different components are there, and then how they can communicate with each other. So you can see that this is the hierarchy that is shown up here. So there's a network. On network, you are running an operating system. That means obviously your server runs on operating system. On the top of that sits your middleware. And then you have the application components. So obviously the information obviously will be communicated by the middleware. And obviously it has to go through the network. So the middleware will pass that information to operating system. Operating system will give it to the networking, and networks will carry that information, as bits and bytes to another network. So that's another form of connectivity. So basic communication happens at the networking level, at the network level. So here your information is going as 0 and 1. In fact, it goes as frames 0, 0, 1, whatever you want to call it. So it goes like a frame, a frame of of data. So you can call it as a, as it is normally referred to as a bit frame. And this is through where the networks exchange that information. But at a logical level, the operating systems are communicating with each other, because operating systems are using the networks, right? On the upper level, you have the middlewares communicating with each other. So the middlewares is exchanging common services, common information with each other. And through this middleware, obviously, two application components are communicating with each other, right? So this communication of the application component is facilitated by middleware that would translate the information from one format to another format, and make it compatible with another type of application. And obviously, they may be running different operating system. Now here, this is running on like Windows, and this is running on, say, for example, uh, AUX. Now that's a operating system, on one server. It's a Unix derivative, Unix-based operating system. So they are communicating with each other. And of course, the data exchange happens through networks. So the networks only exchange data with each other. So that's how it happens. So, but the important point is that the middleware sits in between the application and the operating system. So this is the middleware which facilitates communication essentially between two different application components here. So this one is running. This component runs on system 1. This runs on system 2. And using this middleware, they will be able to exchange their data essentially by taking care of all different formats and other, compatibility issues that may have that will arise with different data from different components. So middleware provides you the connectivity or the interaction support, where the middleware coordinates interaction between two different components of the system. Middleware provides location transparency. Well, you don't need to worry where a particular component is located. The middleware will take care of that. And the middleware doesn't need to know the physical location of the components. Whether the component is located in the same country or in a different continent doesn't really affect. This is just like your middleware will also identify IP addresses, uh, and it will identify a particular service or a particular component with a specific address. Now, where that is, now this is your logical address. Where exactly is this machine physically placed may not be necessary or needed for this particular middleware to function. So it provides provisioning of the common services. Now, this term provisioning is very important in the information systems domain. So where the middleware provides reusable implementation of the services that may be required by several components in distributed systems. So it does the provisioning. This is, as I say, is a very sort of a specific word used in information systems, especially in distributed information systems, in web-based, or you can call them as, web-based services, or in web services domain, where many applications work through providing web services and through this architecture of what today you call as your cloud computing architecture. So today, many applications use these kind of services uh, more often than not, and they will do the provisioning and they will use some middleware to exchange information with each other. So by using these common services, components can easily interoperate and provide user services in a consistent manner. So that's basically what it is. Distributed systems most commonly would use a client server technology, a client server architecture. So mostly distributed systems are accessed over internet these days, and they use client server systems. Now you already have, I'm sure you have heard about client server architecture, where a user interacts with the, a user interacts with the program running on a local computer. Mostly in today's scenario, the local client is your web browser. So again, to understand, I'll give you example of the, you're using your Google Doc or you're using a Google Drive. So where would you be accessing your Google Doc? Of course, in a browser. So your web browser becomes your client, right? And this interacts with another program running on a remote computer. That means your web server. So this is client server architecture. So you are the client, or you can technically understand that your browser itself is the client. And this client, that means your browser, sends a request to the web server. It sends the requests to the web server. So the web server responds with the particular data that has been requested, and the remote server provides the services such as access to web pages or access to a particular document, like in this case, if you're using Google Docs, which is again formatted as a web page and provided to you on the browser itself. So this is how this whole system works using client server computing technology. So client server interaction happens, as you can see here. All the circles are representing clients, and the squares, or whether you call them rectangle, these blocks represent the servers. So you can see a set of clients are all communicating with this server here. And this server may be communicating with another server to provide some services. As I said, probably this server is trying to authenticate these clients. Now, in order to authenticate these clients, the server will send a like an authentication token to this authenticator server. Normally, there is a separate servers which can authenticate the users over a network. We call them, when we talk about Microsoft technologies, we call them as LDAP servers. You can also Google that, what is LDAP protocol and LDAP servers. It is basically an authentication service where you have a specific server dedicated to authenticate the users and to find, what profile they have, what access control is needed, what permissions do they have to access different resources on the network. And the LDAP server will authenticate them and will provide a list of authorizations or the the permissions they have, or any deny permissions if there are any deny permissions for the resources. And then the server will read that and provide the resources, because the server cannot just provide unless it is a web server and it's a public web, like a web, like a public website. The web server will also sometimes have some restricted sections or restricted, like areas on it, or restricted data present on it, which is only given to specific users when they authenticate themselves. So now this obviously becomes like a intranet and extranets. So, in intranet, it will be a company employee who will be authenticated, and then only information will be supplied to that person. If it is an extranet, it could be a partner, external partner. But then again, authentication is done, and only after that authentication, that information is provided to the remote party, the remote client. So there can be many other kind of engagements between different servers. As I gave one example, that normally happens. There is an LDAP server sitting in a different place, in a different location. So that basically would be authenticating and then giving the information to the other servers. There can be other examples also picked up, which can be providing specific services. Mapping of clients and servers to the network computers. As I see, there is obviously the server computer. There is a network here. This network provides connectivity to the client and the servers. As you can see right here, any request will go to the network and the network will pass that to the server. So mapping of client server on a network computer can be done through different networks. Layered architecture model is the model that is used by client server applications. Normally, we try to understand the client server applications with the number of tiers they have: 2-tier, 3-tier, multi-tier. This is a typical example of multi-tier. On the client side, there is always something called a presentation layer. A presentation layer, basically, if you want to understand, presentation layer would be probably user interaction happening through forms and some menu given to the user, through some links given to the user. So that all is your presentation layer. So you can say a web form that you open or a web page that you open on your browser actually is a presentation layer. Now, when you enter some data into that form, that data will obviously go to a set of files which handle that script. The old technology was CGI, called Common Gateway Interface, right? The new technology has many other handles to it. They have their own. They accept the request using GET and POST protocols. GET and POST. So data handling happens through some script. It could be depending on any language. It could be any script. It could be a ASP script that you use. ASP.NET if you're using that technology. It will handle your POST requests. It could be PHP. That's another technology for handling data. There can be any numerous Java servlets you were used, and then Java server pages, JSP were used. So all that, these are some of the examples. And then you have Microsoft server pages, MSP. These are some of the technologies that are used as data handling technologies that handle the data. And then there is some business logic layer, where you write your business rules. So if you say, you're submitting some data, you would say, okay, now calculate, like say, for example, you have a point of sale system design. Now you want to calculate the bill. You want to calculate the invoice. So you would obviously take all the items that are being bought in your shopping cart, and you will add up their price, multiply by that with the quantity. So that is all application programming logic. So application programming logic, or you can call it as a business logic, is implemented at this level. So you can see there are multiple layers. There's presentation layer, there is data handling layer, there is another application program interface, or some, you can call them as more of like a business logic layer. And then in the end, you have database layer, which is called backend. You must have heard this term a lot. So if you are simply using a basic application, like you create a basic application like a front end application. So there you use term like front end and back end. Now that's a typical example of two-tier application. But when you are designing a web-based application, then you basically have created either a three-tier or a multi-tier application model. So it's a layered architecture model that you are using for client server applications. So obviously your server is your web server. Your database sits probably, it can sit on a web server or it can be a separate server, just a database server itself, which communicates with the web server. So in multi-component, multi-layer architectures, these things normally happen. So this is an example of a multi-layered model for client server applications. Okay, presentation layers in a client server application. I've already explained a little bit, but there's some more information. Presentation layer is concerned while presenting information to the user. So as I already mentioned to you, when you open your web form, that is your presentation layer. Presentation layer means what information is being presented to the user and how it is being captured from the user. So that is taken care by the presentation layer. Data handling layer manages the data that is passed from to and fro from the client. So it can check the data and it can generate web pages also. It can reformat that information that comes from the server and give it back as a web page to it. So basically, this is your a layer which can handle the data or format the data. Application processing layer is where your business logic is sitting. So you call it as implementing the logic of the application. So your business logic, business rules, how you're going to calculate the invoice, how you're going to add all the items in the cart, what tax will be added to that when you are, calculating the invoice. All that is part of your business logic. So your application processing layer will take care of that. And the final one is the database layer, obviously, which stores data and provides the data request whenever it comes. So this is where your SQL queries go through. And the SQL queries are processed, they are interpreted by this layer. And we normally refer to it as backend. We normally call it as a backend. So backend means your database layer, right? Architectural patterns of distributed systems. So what different architectures do we have? Some of that we've already talked about. Two-tier applications. So there can be specific kind of arrangements between architecture of your distributed systems. One is called the master-slave architecture. Now, in this master-slave architecture, uh, normally used in real-time systems, or mostly the legacy systems, as we call them, they use these kind of architectures. So where the server is a mainframe machine, a very powerful mainframe machine. And all you do is you send some request, you send some commands basically. So there's a mainframe server sitting somewhere, and you send out a set of commands using just like a communication screen. Something like your which you called is what do you call that as yeah, like today a shell. So you have heard term called SSH, secure SSH, sorry, secure shell, SSH sessions. Uh, SSH session actually is one. It's just like a window where you can type your commands in. You just connect using connect commands. You would give the address of the server, and using a SSH session, you would connect to the server. So what is happening? You're just sending command. I mean, all your computer is doing is just sending the command to the mainframe computer, to the remote server, right? Using a SSH Windows session, some client that you have on your side. So all the processing will be done by the server, by the mainframe computer, right? And it will have live sessions with all the users when they are communicating with each other. So you create a running session with that mainframe. And only once you terminate your session, obviously that communication channel will be finished. So this is a master-slave architecture used in real-time systems, and in which the guaranteed interaction response times are required. That means there has to be a live session between two machines, the master and the slave. So why it is called slave is simply because that machine does absolutely nothing. This is a bit ironical, when the slaves were there, they were doing all the work. Masters were sitting idle, just waving their sticks around. But obviously in information systems, the things are quite different. That's why I like information systems, where a slave does nothing, and the master has to do everything. So all the responsibility of processing of your data, everything has to be done by the master, which is obviously a very powerful computer like a mainframe sitting and handling the requests coming from the slave. Okay, in a two-tier architecture, client-server architecture, which is used in a simpler, one of the most common client-server system, is where the system is centralized. And then obviously there is a front end, as we call it. There is a front end and then there is a back end. Back end is your database server, right? So the front end is where the user would give the input, and the back end is where the data and all that will go. All the business processing happens on the back end, mostly in two-tier client-server architecture. So which is used for simple client-server systems, as we have already mentioned. And then today we use multi-tier client-server architecture. So which is more popular these days, which is used when there is a high volume of transactions, of course. So say, for example, you are using, I have already shown you the example of multi-tier systems right over here. They have multiple layers. This is a multi-tier system where you have presentation layer, data handling, application processing layer, and database. All these layers are separated with each other. So in a multi-tier application, you can say that they are capable of handling high volume of transactions because they have specialized uh, components, specialized layers that handle specific service, and they are capable of handling high volume of transactions. So multi-tier client-server architecture systems are more popular these days because of the advantage they provide. Then we also have distributed component architecture, which means that certain components will be distributed. That means they will be located in different locations. Now, even okay, in two-tier or multi-tier or master slave, these three are centralized kind of arrangements, right? They are more like centralized. Master slave, obviously, it is most centralized because there is only one master sitting, like one powerful computer sitting, a server sitting in the middle, and other slaves are connecting to it. And every processing is done by the master, and the output is sent to the slave, to the client. In two-tier, there will be some basic input processing that can happen, by the client itself. The client will do some processing, and the server will also do some processing. In multi-tier, this is split up into multiple layers. So the presentation layer is where the client would give the inputs and see the output. And then you have a few other layers in between. One is obviously the your data handling layer, and the other one is your application processing layer, which will take care of your business logic and your data conversion, data handling, converting the data output into in a web server, it would be like converting that into a HTML formatted page into a web page, and then sending that information as HTML formatted information, like a created web page, which is dynamically created, to the user, so the user can just read it. And obviously you have a separate database layer. So this is basically what happens. Now in distributed component architecture, obviously this is really distributed when the resources from different systems and databases need to be combined and implemented. There is a implemented as a multi-tier client server system. So basically, most of the multi-tier client server systems can also be distributed systems. There is another one, peer-to-peer architecture, interesting architecture, which I would also explain to you, which is used when the clients exchange locally stored information, and the role of the server is to introduce clients to each other. So there is a minimum role for the server in a peer-to-peer architecture. Most of the machines are directly communicating with each other, and they are kind of in exchange of information from each other directly. There's no server as such. In many peer-to-peer networks, there is no server. In some of them, there is a server, but the role of the server is very minimal. It's just to kind of like establish an introduction or establish one communication channel between each other. So peer-to-peer, networks. The examples are your your torrent networks. You must have heard about these terms or used them. So your torrent networks, if you have used torrent networks where you can share a data from your computer, and you can also download data from somebody else's computer. Mostly the torrent networks were very, I believe, still popular. I used to use them at my time, but I'm sure you must be using it. Although there are risks of using torrent networks because of the malware being infections being very prominent these days. They were used to download movies, obviously look for movies. So the torrent networks would look for that particular movie, or a book or any information on the computers of the other participating users. So if a person connects to the torrent network, say for example, then that's a peer-to-peer architecture. And that person would obviously, there may be a server sitting somewhere sometimes to provide some information, because that keeps an indexing of the users, and then it can give a list of users who are more active, sharing information, and they can appear on your search list easily, quickly. But their role is very minimal. They don't do any processing, they don't store any data mostly, and the communication happens between two peers directly with each other. So if you are sharing, you're basically sharing or connected to torrent network, any files that you have downloaded will be also then shared with other users, and you will be able to download any file which is being shared by other users. Say for example, a movie or a book or any piece of information can be shared. Obviously, you find softwares, mostly pirated stuff, but yeah, you can obviously when somebody can say it gives it gives encouragement to piracy. Well, in certain terminology, it does actually. There may be some piracy rules being broken, but I remember, one of the stalwarts of open source movement, or rather, his movement is free software movement, uh, who used to say that when somebody asks me what is piracy, I tell them, yeah, it's bad to rob ships. So that's how he would define piracy. In fact, the point behind that philosophy is that many things which have been licensed today and sold
by all these big companies actually have not been developed by these companies. So when you say even when Bill Gates was selling its first Windows based operating sorry it's DOS. The first operating system that Bill Gates created was DOS, MS-DOS, right? And then the Windows came up. Now DOS was a character user interface operating system. Now when he sold that MS-DOS, most of the things that he sold as MS-DOS was actually developed for IBM as PC-DOS. And even when he was developing PC-DOS, a lot of things and technology that he used was already existing, developed by some engineers, some computer scientists, some other universities or organizations like AT&T, Bell Laboratories, and things like that. And they were simply available open in the market. Everybody was using and sharing them. And then come these guys, your Bill Gates and your Steve Jobs. They pick up those pieces, in fact. They probably would have done some improvements on them and then pack them nicely into their own boxes, put their brand on them. One puts Windows, other puts the Apple, half a bit Apple there, and then start selling them. That's exactly what has happened here, right? And they don't own every piece of technology. Those technologies were developed over many years by different computing community out there, the researchers out there, and they simply started marketing them, right? With some improvements, as I said, nothing more. But do they own all of that? I personally don't believe they do. So it's just that how this patent system and this copyright system has come up, which has rather, well, in some cases, it may have protected some copyrights, intellectual property rights have been protected. In some cases, if somebody has genuinely developed something new, novel, it gives them exclusive rights of that. That is true. But what has happened if you look at, especially look at, your information systems technology or your IT world, as we call it, information technology world, uh, a lot of that has been, I believe that has been just misused. So they are not real owners of these technologies. None of them has been developed. Whatever Microsoft sold as Windows NT platform, that was their first network-based operating system, was actually they hired Unix guys. The guys used to program Unix systems, the same system they put out under the name of Windows now. And obviously it was sold by Microsoft as Windows operating system. So this is just like you create your you created your web application and your friend borrowed it from you, change the names, change some, pages there, and then it becomes their system now. So because every piece of code cannot be tagged, cannot be sort of like stamped, copyrighted or anything like that. There was no copyright earlier anyway. So I got a little bit carried away anyway. So coming back to the topic, client-slave architecture are mostly used in real-time systems. The master process is usually responsible for computation, coordination, and communications, and it controls the slave process. So master is basically controlling component there. That is why it is called master. And the slave processes are dedicated to specific actions such as acquisition of data from an array of sensors. Now, I was giving, yeah, tell me.
The you spoke about torrents earlier.
Yes.
So what happens in the case where there are more people seeding than people downloading, or when there are more people downloading than the people seeding?
Yeah, the problem is not with the, and I honestly, I tell you, when I was using it, I was also doing the same thing because I had very limited bandwidth in those days. So if more people are seeding and less downloading, that's not a problem. That obviously will give you high speed downloads, right? And that's what, well, it does come up like that. Probably you would limit your seeding. You can actually control your seeding bandwidth. I haven't used that. I was using that when I was mostly a student, actually, or rather a student come academic, because I was teaching and studying at the same time, of course. And that was the days of 2000, 20 years ago. That is when I last used the torrent networks, honestly. So I don't know what has changed in that world since then. I have lost track of it. I never used a torrent network since then. But obviously that time we could control your bandwidth seeding, that, I would only seed at 1 kilobits per second. And I'm talking about when the networks were very slow, internet was very slow. Bandwidth was a very rare commodity. So I don't know what happens these days, but hopefully, but the point here is it gives you the collective power, the collective effect. So if you have like 100 users, or rather, yeah, 100 users seeding at 1 kbps, right? And that is multiplied by, okay, let's say you 1000, right? Now that becomes 1 Mbps now, right? So you have 1 Mbps, that download can be, and if obviously if there are 50 people downloading it, they will have a download speed of 2 kbps. That's how it is. So you need more people to seed and less people to download, but that's how it is. But in some cases, some of these networks do put some super nodes there.
Yeah,
Now the
so
super nodes, yeah, super nodes does improve the performance because they are, they are actually where, some of the common downloads are actually stored temporarily, and from there it forms like a buffer,
so my
and from
question
that buffer, others can download, and that gives a better download speed. Yeah, tell me.
my question is, because
Yeah.
it's peer-to-peer connection, right?
Yes.
So who manages that peer-to-peer connection? So for instance, if there is too many people downloading than the ones uploading, which computer then decides that, okay, now we have to decrease the speed, or now we have to, or where are those buffers sitting? Is there a
Yeah.
master?
Ideally, a peer-to-peer network is not controlled by anyone. It's just controlled by, obviously, if there are more people downloading, and the more people waiting to download and less people to seed, that obviously will give a very poor performance to the network. You know, this is just like, not many people are participating, volunteers as volunteers, and everybody wants to have a good clean roads. Nobody wants to go and clean the beaches, right? But you want to go and have clean beach, but you yourself are not, that's an example I'm giving. You yourself are not going and cleaning the beaches, participating in the cleaning drive, or rather even polluting the beaches. So if more people are polluting the beaches and less people cleaning them, uh, so obviously you will have a dirty or a littery beach littered with bottles and everything. So that's how it works.
So there's no
Peer-to-peer
computer.
networks are not controlled, but sometimes some people would, like volunteer. Okay, let's go and clean the beach. Let's improve the performance. So they might put some servers dedicated as super nodes, and that super nodes can actually improve the performance because they can become like repositories on their own, and from there people can download things. You know, especially some common downloads can be done through that. So essentially, there is no control, ideally, but some people may volunteer, and then in that case, you might have some super nodes which have two functions. Either they can simply index most active users and share that list with the users who are trying to search for something, or sometimes they can even be like, repositories of some stuff, some data, some files, and they store it and people can download from them. All right.
Okay, thank you.
Okay, so and as I say, I haven't used torrent from ages now, so I don't know how it really it's working, but that's how it is. But there are some good people everywhere. Well, some people would say them as bad people, because some of these, Torrent networks have been a target of obviously the companies who are again, as I say, you know, the philosophical question is out there. After that. Thank you. All right, guys, back to the session. I wonder why it doesn't have a pause recording thingy there. It should have something to pause the recording anyway. Can you see my screen, guys?
Yes.
Okay, great, great, excellent. So, yes, we've been talking about master-slave architecture. So, as I said, master-slave architecture means that the master is in control, does all the processing, and the slave is simply what is called, just like probably like a medium to send input and process and just to receive the output from the server. Some dedicated master slave architectures basically are certain, like specific networks, auto functioning networks. Say, for example, used in industrial automation. And there's an example given on the next slide about traffic control systems, which may use an array of sensors as well. And these sensors dedicatedly send data to the server, and the server processes that data. So this is a typical example of master-slave architecture. So there are sensors which provide, traffic flow data. So there is, traffic flow sensors here, as you can see. They provide the data to the master. And then there's an automated functionality that they provide. They send the data and the output to the traffic light control processor. Now, this is an automated traffic control system that we are looking at. So there are sensors which will provide the traffic data. The master will receive the data. The master will basically then send signals to the light control process. That means your street lights, your traffic lights, timing will be automatically adjusted based on the flow of the traffic. So if it sees that one of particular road is more busy, so then it will obviously automatically increase the timing, the green light timing for that particular road. Compared and to other roads, right? So there's an automatic feedback that happens, and then that obviously control your traffic lights. So that's a typical example of a master-slave architecture. So this happens automatically, without any intervention. So that is why it becomes a master-slave architecture. In a two-tier client-server architecture, basically the system is implemented. There is a single logical server. And then there are a lot of clients. There's a huge number of clients, that use that server. There are also two variations here. One is called the thin client model, and the other one is called fat client model. Now, the thin client model basically is where the presentation layer is implemented on the client, and all other layers like data management, application processing, and database, everything is sitting on different servers on a different server machine, or maybe on multiple servers. So you can call that your thin client basically is very thin, which means it doesn't have much processing power. It is simply like an input-output device, So you're using the keyboard to give some input, or some other type of input device might be used. And then you have a screen to see the output. So that's basically the thin client model. So thin clients basically is like a particular client with minimum processing. In fact, there are many thin client architectures. You can Google it and then study more about it. And computing is one of them, which I used myself, and we did some amazing things from that thin client. One of the good advantage of using thin client obviously is that you don't have to spend much on the client side. You can and you can manage it well by managing the server. You don't have to manage the client, at all rather, because the client is simply an input-output device, nothing else. So even if they get stolen, and that's what happened actually in our case, we had a break-in and I think machines were stolen. Our servers were safe, so they just took away. They probably they were very confused, I believe, when they would have entered that premises. I'm talking about good old days before I was working with the university, UKZN. I was working with a private organization. And they would have been sitting and scratching their head for some time. They said, where is the computer? Because they are so used to see, okay, screen is here. But where is the tower, as you in layman language, you normally call it. Where is that tower? And there is no tower, basically. There's thin client, a small box, a small, a box size of a 2 matchboxes rather, stuck behind the monitor. That was basically the computer. So it was using thin clients. So in that way, obviously some of the systems were gone, but it wasn't much loss in monetary terms, as we can say. Right. So and the other thing is obviously you don't need to manage them. You don't need to worry about that somebody will open the tower and steal RAM from it and steal hard disk from it and all those things, right? On the other hand, you have fat client model, where some or all the application processing is carried out on the client. So like you have your LAN, okay? Now in your LAN, obviously you're using fat client because every computer itself has a tower, it has its own processor, it has its own RAM, it has its own hard disk. All the applications are installed and running on that computer. So that's the fat client you are using in your LANs, right? Obviously, when you're using your laptop, again, you're using fat client because your laptop contains all the processing functionality and the processing happens there. If you are coding using Visual C#, of course, you're using your front end with Visual C#, your processing logic also sits, your application logic sits on your computer itself as in the form in the code that you're coding your forms. So it sits right into your forms in the form of code that you generate, code that you write there, and that's a fat client model. Whereas your database server is sitting somewhere else, right? So you are accessing your database through the your SQL your management studio, your Microsoft SQL Server Management Studio, where you are accessing your tables. So they are being created not on your machine unless you have used the local database client. You're using the local one, like a SQL Express, which is the local version of that. But if you're using a full SQL server, obviously you are logging in remotely to your server. You are creating your database schema. That means your database objects on the server. Your tables are being created on the server, and everything is actually sitting in the SQL server, which sits. You don't even know whether it sits in PMB or it sits in Harvard side of it. I guess more on PMB because we have Fusion handling the servers there. So data management and database functions are implemented on the server. So in a two-tier model, right? And the typical example is when you create your front-end applications. That's a typical example of it. Obviously, as I've already mentioned, in a thin client model, every single functionality, whether it is database, whether it is data management, application processing, all that sits on the server itself. And there is only presentation layer, your forms and all that. That is sitting on the client. Where in a flat client model, your presentation as well as your application processing logic sits on the client itself, and your server only has the database. So that's when you are using your, you're creating your front end applications using Visual C#, like you did in your third years, right? That's an example of it. So the legacy systems use thin client models, and then the legacy system act obviously as a server mainly, and then its own right, and then you have a graphical interface to implement on the client. So that's basically the example of your thin client systems. A major disadvantage is that where there is a heavy processing load is that it places a heavy processing load on the server and the network. So the load is basically on the server and the load is on network. And if you have huge number of users, or if the number of users multiply a lot, then obviously you can see latency or lack of performance on the server as well as on the network side, right? So that's a disadvantage of thin client model. So it can only be effective to a specific number of clients. So it's not very scalable in that sense. Of course, you can change the resources of your server. You can upgrade your network, but that's also it has own it's expensive and it takes its own time, of course. But yeah, it depends on what kind of architecture you want to implement, and then you can use that. So fat client model, well, I'm not still a very supporter of fat client model because I believe the maintenance part of that is very high. I mean, I'm just talking from the, of course, it gives you a better performance, but from the maintenance side and from the investment side as well, I'm not a big supporter of fat client model. But anyway, that is still and has been quite popular because the PCs are, more affordable these days. And yeah, but we do get situations like, and I think this is a discussion I was having with my technical manager, Ashwin Singh, when he had his machine stolen. And I was giving example, and I'm giving some suggestions there because obviously, if you have thin clients installed, probably they'll still steal your monitors because they can sell them, right? But yeah, they don't have any towers to steal and to sell. So that's one part of it. Anyway, in fat client model, more processing is delegated to the client as application processing is locally executed. So that's the point. So it's more suitable for the new CS systems where the capabilities of the client is known in advance. So client server systems where you already know how much what applications you want to install and all that. So fat client systems are more popularly used. It's more complex than thin client model. Well, I would say not that complex rather, but uh, it's more you know it's more demanding maintenance than a thin client model. So you have to constantly maintain that fat client. So that means you have to update it, you have to troubleshoot it, and all those things you have to do continuously. So you're going to see, okay, this system is down now, that system is down now, because it runs on multiple factors. It's like a full-fledged tower. Anything obviously can go wrong there. There can be a RAM uh, gone one time. There can be a hard disk blown or a hard disk crashed or something, or a motherboard having problems. Whereas thin client normally works with very solid state technology. So there is one chip. Through that one chip, the whole client works. Even if you drop it, it normally won't die. It won't break. So that's one advantage. But anyway, it just depends, obviously, in terms of efficiency and other factors as well. So new version of the applications have to be installed on the clients. Now that's where the maintenance comes in. Every time you have to keep on upgrading your clients. You need to keep on installing and reinstalling them and all that that happens. Fat client architecture, a good example of that is your ATM network. Your ATM itself is a full-fledged computer. Have you ever seen it reboot? Yeah, the first time I saw a ATM reboot, I was shocked. I thought initially that these are some very special systems and this and that. When I saw Windows rebooting, I was obviously laughing at it. So probably there was a load shedding power cut, and the UPS, obviously, which is the backup supply, did some fluctuations. So it was like rebooting. So Windows rebooting. I said, oh my God. Now you feel a little bit then worried, oh, okay. You're still running on Windows systems there. So it's basically a fat client. Every ATM machine itself is a computer. It's like like a normal tower, as you have in your LANs. It's just that it has a specific interface, a software on it, and then it has a specific interface with the touch screen and all that. That's basically it. Essentially, in the background, it is the same bloody Windows that all of us use all the time, right? So what happens is these ATMs, they do the processing, they run the applications, and they communicate with the account server. So they will obviously communicate with the teleprocessing. There is a teleprocessing monitor, and there is a customer accounts database. So they are basically the bank servers that we have here, and these bank servers provide the data to the ATM kiosk, to the ATM machines that we have installed there. That's an example of fat client architecture. Obviously, the distinction between fat, sometimes the fat and thin client is quite blurred. The distinction is blurred because today we still have sort of fat, some clients are probably not very fat, and these thin, well, if you want to call them thin clients, they are actually sitting in your pocket. Your smartphone itself is a thin client, right? So you want to call that thin client or fat client, it depends on you, because if you have installed an application on your cell phone, say for example, you downloaded Word, from Play Store, you downloaded Word there, or you downloaded Excel, from the Play Store, from Google Play Store. I'm just giving an example for an Android phone, right? Now this particular application will do all the processing, and then you are editing a Word document on your smartphone. So that processing is happening on your smartphone itself. So it is a fat client because it is doing the processing, but it is very thin because obviously the form factor is very little. And obviously the resources are, because of the miniature technology that we are using today, VLSI technology that we are using today, a very large scale integration. When you have your processors sitting with billions of small, small components on it and doing the processing for you. So the form factor is going very small and smaller, whereas the power of the cell phone, the smartphone is increasing. So you're getting, RAM, which was not even affordable on these computer systems, or PCs that we had at one day, in those days. So today it comes with 32 GB of RAM or 16 GB of RAM. These RAMs were not affordable or even on desktop computers at one time. The other thing is, JavaScript allows local processing in a browser. Your browser, obviously, mostly it's considered to be just a simple, presentation layer client, because it gives you input and output there. But using scripting languages like JavaScript, many of the processing can be done itself on the client itself. So, fat client functionality is there. It's doing the processing, application processing logic is happening on that machine, but without any software installation. That means you don't need to install any specific application for it, because that is happening inside the browser itself because of the JavaScript and technologies like JSON, which does the job for you. So these technologies are there, and then they are very much using the browser itself and doing a lot of processing there. Mobile apps carry out some local processing, as I give example of your Word and Excel, to minimize demand on the network. So obviously it's doing a lot of processing on its own. Auto update of the apps reduces the management problems. So you know your Android or even your iPhone or whatever you are using, there is always auto update that is available. So automatically it gives you a notification that a new version or a new update has come up, and you can easily install that update. So these are some of the things happening out there. So there are now very few thin client applications. I mean, there are no 100% thin client applications, but the point is, uh, the statement again becomes a little bit controversial because uh, practically there is no thin client applications. But if you look at when you're using Office 365 or you're using any cloud-based platform, most of the processing in cloud technology is happening on the server. Whether you're using your phone, right? All your phone is consuming is your browser. All your phone is running is your browser. It's not doing anything else. It's just running the browser. So in that browser, if you have opened up a simple web page, well, it will display that web page for you. But if you have opened up, on that browser, you have opened up your Google document, right? Then all the processing is happening right on the server itself. So again, you may argue that whether still is it a fat client, because most of the cloud-based computing is happening on the server itself. So that is very close to a thin client model. So carried out on the remote server. So that's okay. If you have downloaded a Word application or Excel application, then it is a fat client. But if you are using Google Doc in your browser on your phone, then actually it is behaving like a thin client, because the processing happens on the server itself. When you edit your document, it's actually being edited on the server. When you are, doing any formatting, anything on that document, entering any data on that document, that is all being saved on the server itself, not on your phone. So it's again thin client architecture there. So the line is blurred. What I'm saying is that the line is not very distinct, very distinct these days. Multi-tier architecture and a multi-tier client server architecture, the different layers of the system, presentation, data, application and database layers are all separate processes. They might be sitting on different computers, different servers rather, and they may be executed on different processors. So different processor means that they are probably running on different servers or on different machines. So one machine has the database, right? The other machine has the application processing for you. That is more of like your WebLogic server or your Apache server, and then presentation and data management. That probably would be presentation is again your browser. Your data management may be somewhere taken care by the browser itself using JavaScript, or it can again be another server sitting somewhere which provides that data management for you. So it can be different machines in multi-layer architecture. This avoids problems with scalability and performance if the thin client two-tier model is chosen, or problems of the system management of the fat client model is used. So multi-tier applications are very efficient. They are very scalable because they have specialized computers or machines dedicated to handle specific type of load, whether it is application processing, whether it is database management being done on separate machines. And these are very specialized servers, so they are optimized for that kind of functionality as well. So they have better performance than a traditional thin client or fat client. So this is a three-tier architecture mostly used for web-based applications. Web applications mostly have a presentation layer, which is provided by your browser, right? When you open any web form, any website in your browser, then your browser becomes the client. It sends HTTP request, HTTPS, which is obviously encrypted request to the web server, and your web server does the application processing and data management both for you, right? So example, Apache. There can be other example of Microsoft one is Internet Information Server, IIS. These are examples of the web server, right? And then you have your database server, which is separate. Obviously, your database server can be any machine that runs MS SQL Server, like you use in your case, MS SQL Server, Oracle, right? IBM DB2. These are some of the examples of your database server. So obviously you have three-tier processing. One is the client. Second is the web server, which provides application processing and data management both. And the third one is the database server, which provides database processing and data storage for you, right? So that's basically it. Moving on to the next. There is no distinction in a distributed. So when you talk about distributed component architectures, it says there's no distinction between the distributed component architecture between clients and servers. Each distribute entity, distribute whatever entity rather, each entity that can be distributed is a component on its own. So your client itself is a component, and there can be other layers which can be seen as components. So each distributed entity is a component which provides services to other components and receives services from other components. Now this model becomes more of a sophisticated model, or more of like automated by using web services technology. It's called web services technology, and you actually see some applications of that in the form of cloud services. So web services, where the application is developed as web services, it is actually been broken into multiple services, and these services can be hosted on different machines at different locations. So web services architecture or web services, you will come to these terms SOA, service-oriented architecture, and all that. That is where the application is developed as web services and they are implemented at different locations. So component communication is through a middleware system. That's how it happens. So we will obviously discuss that. And it's that, you can consider every single service being hosted by one component, by a dedicated component. So there can be component 1, component 2, component 3, component 4, whatever, different. And there is a communication middleware which handles the communication between these components, and the clients connect to or try and use these services through the communication middleware. So that is your distributed component architecture. Today, it is very much prevalent, as I mentioned to you, that most of the web applications are developed as web services and implemented on different machines and different locations, and they communicate with each other using this communication middleware. Okay, benefits of distributed component architecture. Well, there are many benefits that it allows the system designer to delay decisions on where and how the services will be provided. Basically, main thing is the flexibility. The main thing that you get when you are having distributed component architecture is the flexibility, that everything is a component and you can
plug and play them. You can, put them together. You can fit them very quickly and very easily, depending on the requirements. So that's basically the typical, the plug and play nature kind of, which is mainly what comes with component architecture. It is a very open system architecture, which allows new resources to be added as required, which means flexibility again. The system is flexible, the word comes here, and it's scalable. Now, these two terms obviously are very important. It is flexible plus it is scalable, right? These two terms define what exactly is the benefit of using distributed component architecture. It is possible to reconfigure the system dynamically. The system is very dynamic with object migrating across network if required. So you can just easily plug and play, you know, uh, put them together and make it work, and change the configuration as you require. A distributed component architecture for a data mining system is given here. So what you see is there are some databases, obviously, which are installed on different machines, different servers. And here you have the middleware, which is your integrator, integrator 1, integrator 2. What is this? This is basically your middleware, right? Your middleware, right? This happens automatically. I don't do this. I don't know. So whenever I use the spend tool, these spikes automatically generates. I don't know. So middleware is sitting here, and then you have your client side, which has a display module, which has a visualizer module, and which has a report generation module to show different kind of outputs to the user, right? Disadvantages of distributed component architecture. Well, everything has its pros and cons, as you are aware. Two major disadvantages. One is obviously the complex design. Distributed component architecture are difficult, for the people to visualize and understand. Well, I think that's not much of a bigger problem, but problem is obviously to develop these systems. But today we have certain architectures, which definitely makes that a bit easy. So you have standardized. Second is you need to have standardized middleware for distributed components. And the problem lies there because most of the companies don't agree onto that standardized middleware. Now, they have started, well, I could say that they have agreed now. But earlier it wasn't the case. I think this author is a little bit, not very updated there, but anyway, it's fine. So they say the vendors like Microsoft and Sun. Now, Sun is not even a company now. Sun doesn't exist as a company anymore. Well, it did some great things. Sun Microsystems' biggest contribution is the language called Java. The language remains. That means the legacy still remains. Obviously, it's one of the most sought out languages, technologies. Java technologies are used on internet-based applications, and which application is not internet-based today? You can tell me, Most of the applications are internet-based applications. So Java technology is the somewhere, running the show, and it was developed by Sun Microsystems, but Sun as a company has ceased away. They used to develop their own proprietary systems like operating systems and all that. There was an operating system by them called Sun Solaris. Plus, I think it also developed some other very pioneering applications. You can just Google that. So they say that they have incompatible middleware. Yeah, it was the case at one stage, of course. Microsoft and Sun. But soon Microsoft understood that they can't be left behind, and they started rather imitating the Sun technology. Everything that you find, or rather most of the things that you find today in your, whether it is Visual C .NET platform or something else, more or less uses the same Java technology somewhere. The names can be different. Implementations can also be slightly different, but yeah, it is there. So you can say that Microsoft has walked down to sun, but there is no sun as such now, as a company, independently running now. So Sun Microsystems is not an independent company. I guess it was bought by some other companies. Microsoft still stays there, but that's how the fact is. As a result of these problems, service-oriented architectures are replacing distributed component service architectures. Yeah, that's what is happening. So today it's SOA everywhere, service-oriented architecture. Everything is being developed as a service, or I should say web service, and it is being accessible through internet, through XML, through XML, and it is being used as a web service. It is again open platform, as I said. So that's basically I wouldn't call it the love of some companies, but rather compulsion for some companies to go that way. So they are going that way anyway because they have to. So the result of these problems is, like, obviously the service-oriented architecture is being used, is replacing the distributed component architectures in many situations, in most of the situations now. So most of the applications that run today run as a web service, uses SOA architecture, service-oriented architecture, uses XML, uses internet to communicate, and that's a well-established fact. All right, so as I mentioned to you, many of the software services you might be using, say for example, you're using some filters in Photoshop. And as I say, you can use many applications as web service. Now, some of those filters will be actually available as a web service from some third-party vendors. You may be using some specific functionality in a particular software, in a particular application. That functionality may be developed by somebody else, and being hosted on their servers, and then using the web service call, they are being utilized by a particular application provider to enhance their functionality, their product services, and all that. So that is what is happening today. Here comes peer-to-peer architecture. I already gave you example of some of those networks like BitTorrent networks. Yes.
I think some of us have to get going now. It's already 12:15.
Okay. Okay. You can leave. I will still finish this lecture, and I'll share the recording. I'm sure Teams automatically saves the recording for you, right?
I think so. Yeah, it's normally found under the files section.
Yes, yes. So you will find the recording anyway, and you will be able to watch it at your own convenience. All right, thanks. Yeah,
Have a
you
good
can
day,
leave
sir.
if you want to. But if you can stay back, if you got nothing better to do, I would rather like you to stay back, and yeah, that's it. Okay, I'll speed up the session as well a bit, yeah, because I'm having around 15 slides remaining, and I'll quickly finish them off quickly, right? So thanks. So peer-to-peer systems, as we already mentioned, a very good example of that is your your cryptocurrency network. Your cryptocurrency network is actually, and I gave one example earlier, which is your torrent networks, right? So your torrent networks, they use peer-to-peer technology. There were some other services earlier available, and then they were like taken down because of the IP rights, copyright issues, and all that. So they also were running as peer-to-peer services. Torrent obviously is also one of the networks, peer-to-peer networks, and at times it is criticized for
providing access to some pirated software or something, or movies and all that, which is some people consider that as a copyright infringement. So that is it. The other one is your cryptocurrency network. So your Bitcoin and all that, your crypto mining networks. So your crypto mining and all that is actually using your whole cryptocurrency network actually depends on peer-to-peer architectures. They are decentralized systems. The computation is carried out by any node on the network. So all the participating computers there are nodes. These nodes all work together, in tandem to provide the whole functionality of that network. As I say, when you do crypto mining, in typically like when you are implementing your blockchain technology, you must have heard about this, that your cryptocurrencies use blockchain technology, right? So blockchain technology is again a peer-to-peer architecture where all the machines keep a record of the of the data that is there. The data or the record is kept in the form of like linked lists. There is a linked list that is being kept, and that linked list record is copied by every node. And as you know, what is crypto mining is basically where one of the a few of the nodes participate in authenticating every single change that happens in that blockchain. So whenever information block is changed, whenever new information block is created or some information is entered, it is verified. And then to verify that, some of the nodes participate to cross check whether the information is, and by doing that, they would do some like they'll try and decrypt some and try to find some answers, try to find, try to decrypt some information and try to find some, that's how they verify the information basically by running, some decryption algorithm and by verifying every transaction that happens. So the verification of the transaction itself is taken care by some of the nodes. They get paid for doing that. So that is why crypto mining is done by some peers. They have specific machines to do crypto mining. These days, lastly, because cryptocurrency has not been doing very well, it has not been very profitable. But earlier, people have made fortunes out of crypto mining. There were times when they were like really, putting up the mining rigs. Some of you have heard about some people putting up those dedicated rigs for crypto mining. So the system is designed to take advantage of the computational power there and storage, and it's basically on the storage, and it's stored on a large number of computers which are connected with each other, very autonomously. There is no dedicated server controlling them. So most peer-to-peer systems have been the personal computers, PCs connected, but because of blockchain technology, as I mentioned here, now we are finding some business use of the technology. So blockchain is being implemented by some banks. Even you may have heard about the news that some banks have implemented blockchain technology and they are using it. So examples, I mentioned about the BitTorrent networks, BitTorrent protocol. Messaging services like Jabber is a peer-to-peer system. Payment systems like Bitcoin, which uses blockchain technology, is an example of it. Databases like Freenet, which is a decentralized database, is also an example of a peer-to-peer system.
Some communication platforms like Viber also uses peer-to-peer networks. And very interestingly, I wanted to show you this, but unfortunately, uh, the system is temporarily, looks like temporarily not functional. But the system is called SETI at home, and it's a very interesting concept to understand a peer-to-peer system. Now, what happens is, although it's not a full peer-to-peer system, they have their own servers, but most of the network functions in peer-to-peer mode. So basically, what you do is when you download, when you subscribe to SETI at home, obviously you create an account there and you download their client. So once you download their application, your system is given some data to analyze, and this data is some radio signals. So SETI has their telescopes radio telescopes sitting, in many locations around the world. And what they do is they collect a lot of data. Basically, what they're doing, they're looking for ETs, extraterrestrials. They are there to find some aliens for you, right? So you can also participate in that research. You can actually become the ET hunter yourself by providing your computer system processing power to them. So once you download their application, to show that to you, I would show their website. Oh, really? I thought I just closed it. So yeah, my computer is very slow because it runs on very little space. So that's the thing. If you see, this is the website SETI at home. Now there's a message here that SETI at home is in hibernation. We are no longer distributing tasks. So SETI at home message boards will continue to operate and will continue on the backend data analysis. Maybe we'll even find ET for you. So basically what is this platform is all about, as I mentioned, that once you download their application, when your computer is not really fully utilizing your processor will be given some data automatically by the servers from the SETI, and your system will do some analysis of the data automatically. So say, for example, one or 10,000 people subscribed to this, or they kind of like voluntarily joined this network. So now you have 10,000 processors working, for analyzing the data, the radio signal data that comes from this organization, SETI. So it is basically a scientific experiment by UC Berkeley that uses internet-connected computers in search for extraterrestrial intelligence. That is basically the full form of SETI. You can participate by running a free program that downloads and analyzes radio telescope data. So radio telescope data comes to your computer and it gets analyzed, and then the output goes automatically to the SETI servers while you were watching your movie, on your computer. So obviously, some of the resources or processors processing power was not being utilized. So that can be like donated in a sense to the SETI in that case to analyze their data. So these kind of initiatives, as you can see, can also contribute quite significantly to the scientific research, scientific endeavors of some company. So while you were thinking that you were simply sitting and watching some soapy on your computer, or playing one of the games, one of those very, I would say one of those retro type of games, old kind of games, which are not very processor hungry in terms of their consumption of the resources. So in that case, you actually were also participating in some research endeavor from Sydney. So that's the interesting part. So this kind of participation can also make significant progress to the research community, where people can donate their processors to them. And that means, as I say, if 10,000 people had their processors power donated at one stage, it's equivalent to like a supercomputer, um, a small supercomputer, which basically is very difficult to and very costly to procure. While this type of processing can be done by contribution of people, by volunteers itself. All right, so the logical network architecture of your peer-to-peer network is decentralized architectures, and then you can have semi-centralized architectures. Semi-centralized architectures means there will still be a server, but server won't do much of the work. The server job would be more of like like a indexing server, trying to link nodes with each other, help the nodes to connect with each other mainly. It kind of like a connecting link between nodes. So that's how it is. Application architecture, the generic organization of the components making up peer-to-peer application is the application architecture. So we're not talking now when we talk about application architecture, we are talking about SOA, services oriented architecture. You can study more about that and so forth. So you can discuss about it. Yeah, so that's basically it. And then we are talking about more about network architecture. So this is the network architecture. Our decentralized P2P architecture would be like many nodes participating with each other. These are all nodes, and then they kind of like obviously participate in the network with each other. So that's basically what it is in peer-to-peer network. In semi-centralized P2P architecture, you can say there is like a that's what in BitTorrent networks, they are called super nodes. So these super nodes, basically are like some servers sitting in between, which sometimes help the nodes to connect with each other. Sometimes they also serve as repositories. They can called as mirror servers, where they keep some data, they act as repositories of their side, and other nodes can communicate with them. Normally done to somehow like improve efficiency or manage a particular network, so it doesn't become too much disconnected, and it doesn't become like too decentralized, so to an extent that it stops working or the performance becomes too much on the lower side. So that's basically sometime that there's some semi-centralization is done to improve the efficiency of the network. Yeah, software as a service, which is obviously known as SaaS. Today, when you talk about cloud computing, right? You are using software as a service extensively. So in cloud computing, all your cloud computing application use software as a service, and they use software as a service is also being developed using an architecture called SOA, service oriented architecture. So service oriented architecture is being used. This is more of like an architecture, a developmental platform, and a developmental strategy. Software as a service is basically application available as a service, and we see the implementation of that as a cloud service, normally referred to as cloud service. So this cloud is no new thing, no miracle, or Nothing is just, sort of a, you can call it as a, renaming of some technologies which already existed, but more of like today they are being available through internet, through your browser. So since it is being used and being accessed somewhere on the internet, you don't know where the server is. It is like there's a high level of abstraction that is there. You don't know exactly where the server is and how many servers are there. So simply we refer it to as cloud. It's out there in the cloud, it's like out there in the internet. But behind that, there is distributed architecture. Behind that is the software as a service as one of the technology, and basically your service-oriented architecture as a development strategy, development platform. So these are the terms that are running behind the show. You need to understand that. Otherwise, yeah, these are all the fancy terms that you normally hear about them every single day, and you use them extensively as well. So when a system is computationally intensive, so what is basically, and it is possible to separate the processing required into a large number of independent computations. So how do you use peer-to-peer architecture basically? Okay, use of P2P, peer-to-peer architecture. That's what basically where it comes from. We already discussed about it, but anyway, when a system primarily involves exchange of information between individual computers on the network, and there is no need for the system to be centrally stored or managed. Yeah, that slide is basically, inserted here, although it doesn't belong to this section. But anyway, it's about P2P again. Security issues in P2P system. I'm just surprised. Yeah, we're talking about software as a service, but why we started talking about P2P anyway? Slide seems to be a bit of a mismatch, but anyway. So what are the security issues with P2P? Probably that title is misplaced there. Is that there is a lack of central management, which means that malicious nodes can be set up and they can deliver spam and malware. Now, that's a big problem with P2P networks because nobody controls it. So you don't know which nodes have the malware sitting on them. And when you are downloading that malware gets actually into your computer as well, and that it infects your system. So P2P communication requires a careful setup. Yeah, you have to be careful what you are sharing. You can't share every single folder on your machine because then it will be publicly available to everyone. So you have to protect your information. And if you don't do that, it can be exposed to the peers. So it can be like become a public information then. So you have to be careful when you are installing a P2P network. Software as a service, basically, that's what we are discussing now. It involves hosting of software remotely. Software is hosted remotely. That means it is hosted on some web server. And that service is provided to the user on internet, right? So the software is sitting on a server, probably a web server. It can be multiple servers. Obviously, we've discussed about distributed computing anyway. And it is accessed through a web browser. So these are some of the main things. So the software is not deployed on the local PC. A good example, of course, as I said, Google Doc. You don't need to install any kind of Office software on your machine like MS Office, but still you can create your documents, you can create your spreadsheets, you can create other kind of softwares, other kind of applications can be used, and all that can be accessed using the web browser. Because this software actually is available as a service, through the browser. The software is owned and managed by a software provider. Like in Google Docs, it is Google. The parent company is Alphabet. And software is basically controlled and managed and owned by the organizations that use that. There may be some free access to the software, or there may be a paid access to the software. So you might have to pay based on a annual or monthly subscription, and some service may be available free to you, like the basic Google service. Obviously, a Google Doc and everything is available for free. But it comes with limited space, limited storage for you. 15 GB, I think. 15 GB is the free, space given to you. If you need more, then you have to pay a monthly or annual subscription to Google. So software is deployed on the server or a number of servers, accessed through a web browser, managed by a particular organization that owns it. User may pay software according to as being repeated. Some information is being repeated here. You pay it through the monthly subscription, all right? Sometimes the software is free, but obviously at times when it is free, obviously it comes with the advertisements. You know that you have to accept this advertisements and all that. That is how they make their money, and they give you a free access. So which will fund the software service. So basically, they have an advertisement-based model, or they have a subscription-based model, and that's how they provide you the service. So SaaS and SaaS, they work quite closely together, but they are not the same. SaaS obviously is software as a service. It's a way of providing functionality on the remote server with client Excel through the web browser. All you need is a web browser, and you would be able to access that service.
So
Yeah.
but the time is reached now.
Okay, the time is up. But anyway, I just have got few slides to finish. I will obviously the recording will be available to you. If you want to leave, you can leave. That's fine. I will just finish the session. There will be only a few slides.
But you can't watch the 4 hours or 3 hours recording.
Sorry? What do you say?
We can't watch the 3 hours recording, so it's too much.
Yeah, no, but you can, go through it at your own pace. You can watch half an hour and then have some coffee, and watch half an hour and have some coffee. So yeah, you can watch it at your own pace, right? So now this obviously would be available as a recorded lecture. So you can take your breaks and watch it. That's how it is. Yeah, I know my lectures are long. Unless somebody is standing there to kick me out of the lecture room, I would like to talk. So, I would like to share more information, which I can share with you guys. So that's the intention. But as I say, you can watch it at your own discretion when the recording is completed, right? Thanks.
Okay, thank you, sir.
All right. The server maintains the user data and the state during the interaction session. So basically, there is like a session which is maintained on the server. So there is session management that happens. The technology works in a way like, the session is asynchronous. That means it is not continuously maintained. So whenever you make any change, like say, for example, you're editing your Google Doc. So whenever you make any change to the Google Doc, temporarily a session will be created, instantly rather. And once you have stopped making the change, the session will automatically be terminated. So the session is asynchronous. That means whenever there is a need, there's a session. When there is no update happening, the session is automatically closed. The session is automatically terminated. So that is a very efficient way of managing multiple user sessions and allowing multiple users work at the same time, because the session is not live and it's not directly engaged with the server. So the server, this technology allows server to serve more number of users, numerous number of users using this kind of asynchronous session management. Transactions are usually, so basically in software as a service, they say that the transactions are long distance transactions, long transactions, but that's not true in today's perspective. Most of the technologies, even if you are using software as a service, that's fine. But even that SaaS uses short-term sessions, sessions on demand and asynchronous mode of sessions today to improve efficiency. So it's not like they're using long sessions all the time. You would see that practically yourself. If you're not doing any editing, you'll see that your session will be like sort of like frozen to some extent. It won't be like the clock is ticking for you and the server is waiting for you. It's not like that anymore. So that brings efficiency in the system. In service oriented architecture, which is more of like a platform or architecture development, it's more of a software development platform. The approach is of structuring your software system as a set of separate stateless services. So again, we talk about services here, right? So we are talking about software as a service, and here also we are talking about stateless services. Now, SOA is being used to provide most of the services today. So these may be provided by multiple providers and may be distributed, right? So typically, transactions are short transactions where a service is called, does something, and then returns a result. So I was saying that many of the cloud-based platform uses service-oriented architecture, and the services are available as web services, and they are basically given as stateless services with asynchronous session mode. So stateless means there is no continuous session. There is no continuous session between the client and the server in this example, in this case. So that's basically what SOA is being, different from than SaaS. But today, many of the SaaS, software as a service, is developed using SOA, software as a platform. And a good example of that is your cloud computing applications that you use quite often these days. Implementation factors for SaaS. What is basically main factors that SaaS has? The configurability. How do you configure the software? For specific need for each organization. You can configure your software for each organization's requirement. You can tailor make it for each organization's requirement. You can, put their logos and make changes, tweak the changes according to their requirement. Multi-tenancy means how do you present each user of the software with the impression that they are working with their own copy of the system? It might be like, at one stage, thousands of users are using, the same Google Doc services, but none of them will actually see the data being shared unless you really share the link. They won't see that, somebody else's data being, being visible to somebody else. So multi-tenancy is basically where, everyone get an impression that they are the sole user of the system and they have all the secrecy and privacy which is needed, right? So making efficient use of the system resources. That's basically multi-tenancy, means multiple users can use the system effectively at the same time. Scalability, you already know that now. Scalability is basically when a system is designed to accommodate a large number of users, unpredictably large number of users, at a very quick span of time. I mean, the software is so dynamic that it can handle a big increase in the number of users without any impact on the efficiency of the system, on the usability of the system. So scalability is that property that the application is scalable. It can accommodate large number of users, or it can rather dynamically manage the number of users. So if the number of users is small, it will use lesser resources. If the number of user increases drastically, it will use more resources, and this happens automatically. Automatically, it can start new, virtual machines for itself when it needs more power and more processing to be handled, and that happens quite, quite ubiquitously by the system, by the virtualization technology that we see today. So when we say configuration of software system as a service, SaaS, so we see that application service is being given to the user as different profiles are created for different users. So every user can have their own profile, and they can use that services through their own profiles. So application service, which is obviously developed as a web service, is also provided to different users with different profile configurations. Service configuration means, you can have a branding done to the service. That means the users of each organization can be presented with an interface that reflects their own organization. That means you can put the company logo, and certain corporate colors can be put to the screen, so it feels like it's your own software. It's your own in-house software. That kind of feeling you can get. Business rules and workflows, where each organization defines its own rules and governs the use of service as its own data. So your own business rules can be configured to the services. So that means that particular service can be customized to the requirement of a particular business. Database extensions, where each organization defines how the generic service data model is extended to meet specific need. Your database schema can be designed according to your requirement. So that's basically an access control. Now that's very important, that the service customers, they create their own accounts for their staff. So that means every company can have specific number of accounts for their own staff people, and define the resources and functions that are accessible to each of their users. So, and you can do a very good access control, using this model, where you can specifically design what kind of permissions which user has, and only they will be authorized to use those services. Multi-tenancy, obviously, we talked about that earlier, which means that many different users access the same system. That means you can call it as a multi-user system, and multi-tenancy means handling multiple users at the same time. System architecture is defined to allow efficient sharing of system resources. It must appear to each user that they have the sole use of the system. So that's basically the impression to be given to the user, that every user has the same, they're using the system discreetly, although the system is being shared between thousands of users at the same time. So multi-tenancy basically involves designing the system so there is an absolute separation between the system functionality and system data. So the data is not shared or compromised unless you want to collaborate with somebody and you have specific data available to you. Scalability, we've discussed that earlier, and the points here again reiterate that the applications where each component is implemented as a simple stateless service. Now, how does scalability comes is basically, as I said, once a web service or a particular service is developed using SOA architecture, and it is developed as a stateless service, it can be distributed to a large number of users without compromising the efficiency of that. So that is how the scalability is achieved. So scalability can be achieved by having stateless sessions or stateless access to the service. So the system is designed using asynchronous interaction. So the sessions are asynchronous. Now that's a very important word, asynchronous. So asynchronous means stateless in another terms. That means there is no continuous session between the client and the server or the person using the service. So the application does not have to wait for the results, That's very important. The application does not have to wait for the result or for any interaction, for any kind of input from the user. So when there is an input, the session will be created. After that, the session will automatically be terminated. That's what happens. Manage resources such as network and database connections as a pool. That's a very sophisticated technology that is being used, and it has been there earlier as well. There is something called connection pooling, which basically brings a lot of efficiency to the system whenever you have client-server communication between two systems. Now, earlier, okay, you could imagine that whenever a user was connecting with a database, a new database object was created for them, and that took a lot of time and resource to create a new object. And after the communication is done, the database object was discarded or was rather removed from the memory. That is again a resource consuming process. The other alternative of that is pooling, connection pooling. Now in connection pooling, what happens? That many objects are created and they are actually, the technology is called persistence technology. They persist in the memory. They are like sitting in the memory and waiting. Whenever a request comes, they quickly, one of the object is given to the user to be utilized. The object is populated with the data from the user request and the response that goes to the user. After that, this object is automatically cleaned, but it's not destroyed. The object retains there. So there's a pool of objects that are always sitting and are ready to serve the customer, serve the request from the user. There is no time taken to like destroy or to create new objects. So you can imagine that this is more of like, like you are reusing your coffee mugs. So when you finish drinking your coffee, automatically you place them somewhere and they automatically get cleaned in a dishwasher, right? And other person can quickly come and use them. So that's kind of like reusability, object reusability, you can call it as. And the technology, as I say, is called persistence technology, which increases the efficiency and also increases scalability to a larger extent. Other efficiency that can be done, obviously, is called fine grain locking. Now you are aware of the term concurrency control. Concurrency control means that when a particular user is editing a particular record, that record is locked. If the person is editing the table is locked. So nobody else can access that table until that editing carries on, right? But that is also not very efficient. So fine grain locking, basically, to understand it in a simple language, you can consider that if a particular field is being updated or is being used by a particular user, only that field is locked, not the whole record. So it's basically, the locking happens at a very atomic level, as you can see here. It doesn't happen at a higher level. And that also increases the efficiency because it allows more user to use that particular database object at a particular given time. So that is, do not lock out the whole records in the database where only a part of the record is being used. So if it is the update is happening at a very atomic level, like a particular field, then only that field is locked, not the whole record. So that's basically how you increase the efficiency of the system, right? So the key point again are the same, that the distributed systems can be scaled to scope with increasing demand and can provide services, uninterrupted services to a large number of users without the system failing. That means they have enough amount of redundancy and it allows resource sharing. So it enables resources to be shared with a large number of users. So these are some of the key points. The issues that are considered while designing a distributed system is the transparency, openness, scalability, and security, quality of services, and failure management. Now, these are critical issues to be considered when designing distributed systems. Client-server systems are structured into layers, and you already have studied about that. So there's a presentation layer which the client has on the client computer, and then servers provide the services including data management, application processing, and database services. Client-server systems may have several tiers with different layers of the system distributed on different computers. You studied about 2-tier, 3-tier, and multi-tier systems. All that is part of this, layered architecture. Architectural patterns for distributed system include master-slave architectures, and as you seen examples of that, some dedicated systems like traffic control systems and all that. 2-tier systems, where obviously I gave example of the front-end system, where there is a presentation layer and then there's a server. And then we have the multi-tier client-server system architectures, where you see 3-tier and multi-tier applications. Distributed component architectures, where application is distributed into components which are residing on different computers or servers in different remote locations. And peer-to-peer architectures. So we saw some examples of that, like your blockchain technology implemented in cryptocurrency, Bitcoin, etc., and your BitTorrent networks and all that. We saw distributed component systems, and we see that they require middleware to handle the component communications and allow components to be added or removed from the system. Peer-to-peer architectures are decentralized, of course. We have seen that they are decentralized, where they don't have any distinguished client and servers. They simply have nodes, and these nodes participate in exchange of data, and also they take care of processing of the application themselves. Computation can be obviously distributed over many systems in different organizations. That's what happens in peer-to-peer architectures. Software as a service is a way of developing deploying applications as thin client server systems. Why they call it as thin client server systems? Because the processing happens on the server itself, and the client in that case is just a browser, and it uses internet, and you use internet to access that service. Many cloud-based applications today are good examples of software as a service, SaaS. And here the client is the web browser, as we have seen. Software as a service, SaaS basically uses system-oriented architecture. Although system-oriented architecture can be used in many different other instances, it can be used in different kind of software development, but certain examples, good examples, are cloud computing applications that you use today use a service-oriented architecture behind the scene. Although there are other examples of it, like your DevOps. DevOps uses service-oriented architecture. So that's a good example of service-oriented architecture. I think with that, I finished this lecture. Thanks very much. You can go through the session at your own pace. I know this was a very long session. I wanted to give you more information, interesting information, to kind of create some sort of understanding of some of the technologies that you use every day. You refer to them in different names: cloud computing, SaaS, software as a service, etc. But essentially, what is behind all that technology is distributed computing and distributed engineering to develop these kind of technologies. So thanks on that note, and have a great day.